all the people who could make it today. I know a few people had class, so being considerate for them. Okay, I think you all might have gotten the notification that we started recording. Welcome everyone to the first of 3 sessions of our Night Hacks Foundation Exam Workshop for FE 2024. We got a lot going on here. If you look at this chart in front of you, for all the people who just came in, this is basically the poll results. As you can see here, 68 out of 97 of y'all wanted us. We're very adamant on us doing everything. So, as well as a yes, my lord, and backtracking is not on the FE, by the way, so I don't have to worry about this. And stack-related concepts will also be going over in stack, so no worry there. So first thing I'm going to do is I'm actually going to go over the little document we sent out. If you have looked at it, it's fine. If you haven't, it's also fine. All I really wanted to say is to look over the itinerary that we have ahead of us. So today is the first day, Tuesday, 5/14. Throughout the duration of the rest of this session, after I go ahead and kind of talk about everything beforehand, we're going from a dynamic memory allocation up to recursive coding. We're going to leave recurrence through AVL for Wednesday and bitwise onwards for Thursday. Before I start getting into everything, I know this is like a typical thing to say before any lecture, but ask questions for sure. The biggest difference that this workshop makes from going on YouTube and looking up one of the infinitely many foundation exam workshop series that have already been done by other RSOs is the fact that you are here and you can ask questions. I will be frequently putting polls or little sorts of questions going on into the chat and stuff like that. Interact with those because that really is what's going to make the difference. That's why you're here on a 2 p.m. on a Tuesday. So do that. And to all the people who are watching this recorded on Zoom afterwards, I'm sorry, but skill issue, I guess. I don't know. The foundation exam is broken up into 4 parts. I'm going to go over this briefly because I feel like most of you have already kind of scoured the internet looking for things of this nature, but we sort of went over the structure that they have publicly available on the foundation exam website and sort of like put it up against some of the past exams that we've seen and kind of came up with this formula. So the foundation exam is 12 problems across 4 sections. We will have 2 hours to complete all 12 problems, and you can do them in whatever order you want. That was a question that I had answered. It's not like SAT where you have to complete English and then complete whatever, right? So if you get like a really like monstrous recurrence relation problem, it's okay to go to part D and solve all that and come back. So this is the breakdown of what each problem will be and in order as well. This vertical bar right here is basically saying like the second question in part A. These realistically should have been numbers and not dashes, but you get the point. Second question in part A will be a linked list tracing or coding. And so, feel free to look over this on your own, but I won't really harp on it for too long. We will be going over questions in our sessions that are taken from the foundation exam, and we try to grab as many diverse problems and the most frequent type of problems to go over with you all, just so it's relevant and applicable. With that being said, I'm just going to go ahead and jump right on into the presentation. So I already went over this. This is literally just a screenshot of what I was just showing you all, so we don't really have to go over that for too long. And that brings us to dynamic memory allocation right off the bat, going over quote unquote the easier stuff. But do keep in mind that some foundation exam problems in the past that are the DMA problem, the first problem, some of them still have like 40 to 50% pass rate. So although this is like the quote unquote first thing we learn, there's still room for error, and that means there's room to improve. So we're going to go over that first and try to get like a good foundation set up for that pretty much, as well as some tips for solving the problems and how not to flub them up. So Malik, Calic, Realic. This probably feels like a broken record. You guys have seen this a lot. but there are a lot of little specifications to kind of go over and to talk about. So the difference, malloc and calloc are very similar in the way that they're applied. Realic is a little bit different, but the biggest difference between malloc and calloc, other than their syntax being slightly different, is the fact of what they do with the memory, right? So Malloc's memory is uninitialized, which means that it is unsafe to like use. Um, so that really is the biggest difference. In this case, if you're allocating an array with malloc, all of the values in there are uninitialized, so you wouldn't want to access them before you instantiate them, which means just setting a value to that position. Calloc, however, does zero initialized memory, so that makes for safer practices if you're doing some like niche thing. But the biggest thing, they both return a pointer or null. This is important to remember. The null pointer can come up in conceptual trick type questions when it comes to malloc and calloc. Same thing with realic. A null pointer can be returned from all three of these functions. And that essentially just means that there isn't memory, there isn't space to allocate memory, right? Which is something that very few of us are actually going to run into when doing any assignments, or even if we end up using C professionally, given how cheap memory is these days. But it's still something good to know for quote unquote safe practices, because everyone's obsessed with how safe things are. The difference between malloc and calloc, syntax is a little different for the parameters. Calloc actually takes two. It takes the number and then the size of one of that type, whereas malloc they want the size of the whole thing. So basically, the best practice is to multiply the size of one of the things inside of the memory, and then just multiply that by size. So that's the biggest difference between these two. One thing I do want to point out, and this is going to come up later in the tip section for these types of problems, is that the degree of the type it returns that it's being casted to is always a degree higher than the size of the type that we're working with here. I'm going to go over that more in the tips, but that's something I just wanted to plant in your brains now, that there is a relationship between this that you need to follow, because that relationship is where most people lose points. Same thing for calloc. We're getting the size of a given type and we're casting it to a type pointer. And then realic is a little bit different than these two. It doesn't just allocate memory. It actually, believe it or not, it reallocates memory. So it still does create uninitialized memory. It creates, I should have put a little arrow, creates new uninitialized memory. But same thing as before, it returns a pointer or null. And what it will do is, let's say we have a pointer of size, I don't know, 10, and we want 15, right? So we basically reallocate. And we'll basically extend the contiguous sequence of memory to accommodate for anything else that you need. Realic is a little more niche. We don't really use it too much. It does come up sometimes in array queues and whatever, but it's a little more. I'm not going to say irrelevant, but you get what I mean. So, along with obtaining memory, we also have the issue of managing it and ultimately freeing it. And to answer the question in the chat, yes, these slides will be available after the review session is over. So as I was saying, freeing memory is another important part of working with memory. And there have been problems in the past that will ask you conceptually what type of memory violations have we seen. So I'm going to go over this too. The free function, you basically pass in a pointer as you might expect it. I mean, we've all done this before. And that memory basically is freed. It's no longer owned by the pointer, and thus it's either uninitialized or being used by something else in your computer, and therefore memory that you are not allowed to access within the scope of your program. So there's a lot of ways that you can have some really unspecified behavior or some type of seg faulting if you use freeze inappropriately, right? So the biggest one that tends to happen is a use after free. Basically, the biggest time this comes up right here, imagine that this is instead of a pointer, it's a linkless node. This is a very, very common one that you'll see with memory. Essentially, you're freeing the linkless node and then freeing the data it points to. Imagine that this data were a pointer to another type of struct or something. This is not allowed. So the best tip, the best rule of thumb for freeing is to always free in the reverse order of allocation. So for example, if you were doing a 2D array, you would first create the pointer for the 2D array, and then you would declare each pointer in a for loop. And then when you're freeing it, you would declare, or you would free all of the pointers in a for loop and then the double pointer, right? So it's a reverse relationship when it comes to freeing this way, because that is where a lot of the free issues come up. Another one is a double free. This is kind of similar to a use after free because you're trying to free something you've already freed, so you're kind of using it, quote unquote. But this is another one that comes up quite a bit. Typically, when you're kind of freeing procedurally in a loop, this kind of behavior can happen in some off cases and stuff like that. So keep in mind that double frees are also a thing that happens. So here are some of the common mistakes that you can see and can make yourself with DMA that I've done by accident and seen grading friends' papers. Is that these are basically the common mistakes, right? The biggest one is a mismatch of data types, right? So for example, here we, as I mentioned, and I'll go over this more now, if you think about pointers as degrees, right? A double pointer, what is this typically called? Most practically, this is a two-dimensional array. A single pointer is an array, or a 1D array, for being more specific. And then just like, I guess, kind of like, what it's holding, the last data type, right? So it would almost be like a 0th dimension, which makes this a bit funky, but bear with me. In this case, well, like I said, back here, the type that it's being casted to is always one higher. So this is a degree of 1. This is a degree of 0, right? There's a greater than by 1 relationship to the type that we're casting to. In this case, that is not true. So the first thing that we notice here is that this has a degree of 2 and this has a degree of 1. Not only is this improper typecasting, but we're also returning this to a two-dimensional pointer, right? A double pointer. This right here is a conflict. This will not work, right? This is one mistake that we can kind of see. There's actually two mistakes in one, right? Another thing that comes up a lot in these problems is allocating strings, right? If we have a character pointer in any type of struct, that means that we are getting a word, a string. But the issue with this is that there is no memory allocated to this character pointer yet. And so what happens sometimes is you'll string copy into a pointer that basically has no memory. This word has no memory. String copy operation will not work here. Also, 2D array allocation tends to be a bit tough as well. I don't have an example to the right, but what the biggest issue is, sometimes a 2D array will be allocated. And then immediately after that, actually, I did do that. Immediately after that, you try to access I of j. Remember that as you loop over each of the arrays in the 2D array, you still have to allocate the array at that ith position, right? So in this case, we, assuming this is the 2D part is proper, we didn't allocate 2D array of I before assigning a value inside of j. So this is another one where there's a lot of issues that tend to come up that could be an issue on the exam.
You got some
Another,
questions in the chat real quick, Dylan.
uh, do we have to cast on the FE? To be entirely honest with you, I don't actually know. But in my personal opinion, it couldn't hurt. It does help you keep track of kind of what you're casting. And it also helps you identify mistakes like these when you're kind of proofreading and debugging. But I don't think it is required. However, yeah, you can, but you don't have to. Um, you don't have to. My overall stance on it is that I'm gonna do it, unless you have some like crazy big handwriting and really need to save space. But I would advise towards doing it. Another thing, back to the common mistakes. Another big one is assigning data to a pointer and not an address. This is it right here, right? We're assigning an int pointer into an integer. This is especially wrong, right? But this is kind of similar to this issue up here, right? Kind of the same gist. And then last but not least, I didn't have anything up here because there's a hard way to make an example of this, but leaving struct, this should say pointers. If there is an init function and they just want you to allocate memory for things, if there is a pointer, they respect you to put memory, right? And so yeah, you probably want to kind of almost create a checklist on the struct. What I do in the init function problems is that as I go down allocating in each step of the function, I'll check off the pointers in the structs as I go. Because, for example, leaving like not allocating a word pointer is kind of this, leaving a struct pointer unallocated, or the ith array at a 2D array is another one. Um, Another issue that I didn't write, that I'm not going to draw out because writing with this is terrible, but allocating memory to things that don't need memory allocated. There are some cases where you will have a struct that will have like a character array of size 10. This already has memory allocated to it. This is not a pointer. This is statically created once this struct is allocated. So you do not need to allocate memory to static memory. The same thing could be said about, an integer. If it's like just an integer, like wage. I mean, they don't typically make us allocate memory to integers, but you get what I mean. If there isn't a pointer, there's no that you should not try to allocate memory for things that don't need it. And conversely, make sure that you allocate memory to everything that does need it. So again, I sort of went over all of these in the last slide as I was talking about the mistakes. But first things first, you want to create that checklist. Leave no pointer without memory allocated to it. Allocate no memory to non-pointers, as I was saying with the static variables. And then make sure the type is 1 degree higher than the allocated type, which is my example here and back here, right? Pay extra attention to 2D arrays. This one is important because if they're not giving us an init function, which is probably what they will give us, but don't count on that. It will be some type of 2D array problem where there was one they wanted like a Pascal's triangle array where it was like 1 1 and then like I forget 1 2 1 and then you kind of get the gist. It's like 1 3. I don't know. I'm not drawing out a Pascal's triangle right now. But if that is the case, then all of the DMA-ing in the DMA problem comes down to this: allocating memory to the 2D arrays and making sure everything's the right size. Another one is not to forget. It's a +1. Don't forget an extra character when you're allocating for strings to account for the null character. When you do so, for example, like when you're malloking and you're doing string length of a word, that is going to give you the length of the word, not including the null terminator. So when you want to allocate, you need to do string length of word +1 for the null terminator, and then times the size of a character, right? Imagine that's the size of character. My handwriting's small or big, right? That's another thing that kind of comes up when you're allocating improperly and stuff like that. And then last but not least, the biggest indicator of what you should be doing is your function return types. If the function declaration for the problem that you're writing is int int star star, you should not be returning an int pointer. You should be returning an int double pointer. So yeah, keep that in mind as well. That being said, I'm pretty sure, yeah, we're going straight into problems. Before I move on, I would ask if anyone has like any questions at all before we like get into this. I see the chat's blowing up. Here, let me read, see what's going on here. Can I leave the data type of a pointer in the malloc? Okay. But can you explain the difference between dot and? Okay, no, that is not trivial. Yeah, that's something else that comes up. So really quickly before I get into this, the difference between dot and arrow, and that is actually going to come up in our next problem. I'm going to use this as like my little canvas. The arrow and dot operators are essentially used to access members of a struct. So let's say we had a struct and this was a person. I'm just going to call it P for the sake of this, right? And we'll have an integer of age. And then let's also throw their wage in there as an int. So we can like do our little TC flexes on them. And then boom. If this struct, so like if you were to declare, and imagine we typed def this, it was like, and then P1. To access this person's wage, it would be P1 dot wage, right? Oh, also wage and age, that rhymes. That's crazy. Uh, however, this is static memory right here. We have declared it this way, right? This is static. If we had done for person two, we make a pointer and we do a bunch of allocations there. We allocate a pointer to a struct here, and then we do malloc, blah, 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 right? Imagine this is just a bunch of blah, blah, blah. This would be P2 pointing and then age. That's basically the difference, if I'm not mistaken. So someone fact check me here, Loon. This look good, right? Is the difference is if it's statically allocated or if it's dynamically allocated, if it's a pointer or if it's static.
Yeah, that looks good to
Yeah.
me.
So yeah, if we were to malloc this person pointer to access its age, we would have to do this. If it was statically allocated to access its wage, we would do this. I would honestly, honest to God, the best way to remember this is, yeah, imagine that I did malloc space for the struct here. I just didn't want to write that whole thing out. The biggest difference is if you're using a pointer, this is a pointer if you squint hard enough. So that's kind of the best way that I remember it. But yeah, so that's that. I think with that being said, I think we're all good to move on to the problem. So let me close this and then get back to FE prep. Plug for is Danny here? I know Caleb's at Meta right now. Plug to the FE prep team. If y'all haven't used this yet, it's kind of hype. Lets you kind of go over problems, but we pick some out ahead of time just for this. So yeah, as you can see here, we have it. Can everyone see this all right? Is it a bit small? Do I need to open it into another thing? Are we all good that this is visible?
Looks good on my end.
It looks good on your end. Okay, cool. All I'm saying is, y'all at FE Prep, you got to work on this. You should have added like a resize here. All I'm saying, okay. Anyways, as you can see here, this is a 57.3% average, and I want to make it 100. So apparently there is a way to resize. It's not that deep. It's not that deep. Okay, so reading through the problem, this is again just a kind of basic init function, essentially, right? All it wants us to do, we'll go ahead and read it. The struct monster list maintains a list of monsters using a dynamically sized array of pointers to a monster. Okay, that is a mouthful, but as you can see here, we have two different types of structs, not just one. We have a monster list, which holds a double pointer of monsters, and then the actual number of monsters inside, right? And then the monster Apparently, details are not necessary to solve the problem. We don't actually care about what's inside of the monster for the sake of this problem, and you'll see why in just a sec. So a function prototype is given for a function initialize monster, which takes in a pointer to a monster that must already be pointing to memory that is allocated. Okay, and then fills that memory with the information about a default monster. Write a function get default monsters. This one's a mouthful, which takes in a positive integer n and creates a pointer to monster lists, allocate rooms for it, and then fills it with n default monsters, and then returns a pointer to the monster list created. You must call it initialize monster in your solution. Okay, so basically, we already have the initialize monster function here. It initializes the monster pointed to by a monster pointer to be the default monster. This is such a tongue twister. There's so many monsters thrown around in here, but yeah. Let's see. So basically, the first thing that we're gonna want to do, I'm gonna be writing the solution in typing over here, just because, good gracious, I'm not using a pen to write in. I don't even know if I can because I'm not on the Google Slides anymore. But the biggest thing, again, I want to emphasize is that this return type is of a monster list pointer. So let me go ahead and just copy the function declaration over here. It's a bit hard to navigate it. There you go. All right. So like we literally, oh my goodness. Okay. The first thing we're going to do, because the return type is of type monster list pointer, is we're going to, you guessed it, allocate a monster list pointer. So monster list pointer, we can call this res. We're going to use malloc, and I'm going to typecast that because I'm not going to ignore what I preach. And then malloc size of monster pointer. And then after that, we are going to multiply it. Or no, monster list. And that is where I got tripped up with this problem a lot, trying to remember the different structs and whatnot. So let's make this smaller. Okay, so we have our monster list. I'm gonna space this out here to make it look a little better. At this point, we are going to sort of come over here and go through the checklist of, again, we've created a monster list. What do we need to fill in for a monster list? What pointers are there to be allocated and stuff like that, right? So first things first, we can fill out the num monsters. We're going to call result. And because we allocated this, we are going to use an arrow accessor, and we're going to access the results num monsters. And we're going to set that equal to n, because if you remember the problem spec, this is the amount of monsters that we want to allocate room for. From there, we now have a monster double pointer. So first, we're going to do result m array equals, and we're going to need a monster double pointer. So again, you could not cast it, but it is definitely easier to see what's happening here if you did. So we're getting a monster pointer. We're then going to allocate the space. We will need to allocate enough room. Are we allocating monster pointer or monster in here? If people can just drop in the chat. Give it a few seconds. Okay. So we got two monsters and two monster pointers. The chat is acting terribly for me. It is not auto-scrolling. This is annoying. Okay. So the mass consensus is monster pointer, and that is going to be correct. If you remember the trick, you always want this to be 1 degree higher, but also conceptually speaking, a monster pointer is an array of monster pointers, right? So yeah, we're doing size of monster pointer. I was expecting someone to say monster list because I confused the two a ton while we're writing out this problem. But yeah, so we now have all of the fields for all of the result fields are now allocated. At this point, we're kind of done filling this out, except for the rest of the monster array. That's basically all we have left. So with that being said, remember, pay attention to 2D arrays. We are now going to have to iterate through that 2D array and fill out room for more. So we're going classic I equals 0, I is less than n, I plus plus, classic for loop. And then here we are going to first, what is the first thing that we need to do is we iterate through a 2D array that is dynamically allocated. There is something very important that we need to do before we do anything else. I have no clue what that is. Semicolon, oh, that's damn. Anyone? What is the first thing that we need to do right off the bat? No, that is the not the first thing that we need to do. Accessing result of I, as mentioned on the slides back here. No way, the notes don't save. That's devastating. Anyways, you don't want to access the array, the arrays in the array without first allocating room for it. So we do need to allocate memory for that position. So we're going to do res of m array at I equals, and again, this is going to be of a monster pointer, okay? Because we now have, this is a monster double pointer. As we iterate through it, we are getting a monster pointer. You could also think of the whole degree thing as you iterate something, you are dealing with items that are a degree lower. But that could just be me like math braining this out, and that might confuse people more. So if it confuses you more, don't care, don't listen. We're going to malloc size of, and now I'm going to ask you all again, is this going to be monster pointer or monster? Monster. Okay, consensus. Awesome. So we now have our array at that specific position filled out. So now we can actually work with this. So let's go back to the problem spec. It basically says that we need to fill information with the default monster. If we look here, void initialize monster takes in a monster pointer and it's void, so it doesn't return anything. It just modifies the memory. So with that being said, now that we've allocated space for that specific section, we can just call initialize monster, and it wants a monster pointer. So we could just pass in marray at I. And we know that this is going to be fine. We know we don't need any ampersand or anything because we very clearly cast it here. And again, casting coming in clutch. I'm a big casting fan, although I know it's not necessary. We know that this is a monster pointer because we casted it this way. So we know we can just pass it straight in. We don't need to do any fancy ampersands, any addresses, anything like that. It's exactly as we want it and how we need it. And then are we done? Am I missing anything? Good. Perfect. Again, you want to go ahead and return because as we see here, our type is monster list pointer. We're going to go ahead and return a result. And at that point, what is your consensus, everyone? Does this look good? I got a question from Adam. I made a separate monster pointer after the malloc statement. Then I set m array of I to monster pointer. So here, Adam, let me walk through this. So you created a monster pointer this way. So you said monster pointer equals and then you set result of m array at I equal to monster pointer. Is that what you did? Before that, you initialize and then set equal. Oh, so you called initialize monster on monster pointer and then set that. I think realistically that should be fine because they're both pointing to the same memory. The same way that if you actually if you assign them to each other and then freed the monster pointer, the memory that this is pointing to would also be freed. So yeah, that works. That is fine. Just it's perfectly fine. I'd say the rule of thumb is try not to waste ink by being too extra with what you're writing, but honestly, that's fine. It's not bad at all. Yeah, I'm gonna put it back here, and then we go. Oh, damn! There's no redo button. That's crazy. Do y'all remember what's on there? Here, I'm gonna go ahead and finish this up. Res of m array and I equals monster And then lastly, we return result. Everything looks fine and dandy. So bottom right corner, bro. Oh, that's crazy. Anyways, don't worry about that. Don't worry about that. Cool. So that's about it for that. If we flip on the solution, uh, as you can see, we have a near identical. How crazy. Pretty similar outcome. One thing that I will say in terms of foundation exam, are y'all able to raise your hands? I wonder. Uh, just drop a me in the chat if you can't. How many of you have actually ran through a foundation exam on your own and graded yourself? Okay. All right. All right, that gives me faith. Lots of y'all. Okay, good. I personally recommend is that okay, Adam. I personally recommend that as my favorite way to study. But one thing I really wanted to point out: look at all the partial they give. Like, it's kind of crazy. So keep that in mind. If you don't know a problem, like if you genuinely just don't know a problem, and I've encountered problem problems as I'm doing my own foundation exams where I'll look at it and I'll literally know nothing. I will just start writing random stuff and I will get points. Like there was one like crazy like recursion problem like a few years back and I just wrote a for loop calling the function and I got 4 out of the 10 points for that problem. So just write stuff, genuinely, just write stuff. Um, is it true they can only give you points and not take away for something you wrote? Yeah, they can only give you points. If you write a bunch of like, random stuff, they won't take things. It's yeah, there is no penalizing at all. Just write, you know. Um, so yeah, feel free to literally just kind of like cheese your way through the exam for things that you don't know. Uh, it'll come up tomorrow when we go over recurrence, but I think like half of the points for the recurrence problems is literally just the first 3 iterations. So literally just even if you don't know the final answer, yeah, just yap on the FV. Um, so yeah, as you can see here, like 2 points is a 10-point problem. If you allocated everything for the monster list array and then forgot how to loop and do all that, you're automatically at half credit. 2, 2, and 1. Right. So like this right here is the other half of the problem. So yeah, that's all I gotta say on that front. You don't even have to beg, just put stuff. Yeah, pretty much. The notes mention taking off points from full. So, for example, take off an integer number of points for 2 small errors that you believe are worth and less a point. This is basically saying if they got the solution like almost right, this is another way to grade partial. You physically cannot get negative points. There's no way that you get negative points. This is more like bigger picture. If they have some like logic errors, like if for whatever. So, for example, here's a good one. If they did this loop for whatever reason before they did this, obviously, even though they have all of the points here from doing that, there still is some errors there. So it will say 1 dot instead of 1 arrow, correct it and give it full credit. So good thing we went over dot and arrows. There is actually a spec here on DMA. So okay, deep breath. It's been a long day already. On to the next one. We're gonna go ahead and do the next problem that we set aside here, and that is where is it? Employees. Okay. We have our employees problem here, and then let's see. You can shed. Yes. Just going through the chat really quickly. All right. So let's get into this one. Okay. This one, almost similarly to the other one, is a 59.8% average, which is not bad. But we're going to make it 100 here at NIHAX. I want every single one of y'all to get 100 on the DMA problems. Yeah. So as we see here, write a function create employees. So again, this is a simple init function that takes the list of employees' names, list of their salaries, and the length of the list as parameters and returns a pointer to a dynamically allocated array of employees storing the relevant information for emp count employees. What it's basically saying is, okay, we're given the amount of employees we have as well as information on them, and we just want to allocate employees and populate everything as we need. The function dynamically allocates memory for emp count number of employees and assigns the name and salaries for each of them from the input parameters. During this process, the names are stored in the dynamically allocated memory of string type, and also make sure you assign the length of the name appropriately. This is them literally telling you, hey, don't forget the null character. That would be bad. So, yeah, your code should use the exact amount of memory needed to store the corresponding names. Hey, don't just like add 5 because you think the null character should be there. You assume no name is longer than 49 characters. Okay, cool. With that being said, yeah, we can get straight into it. The reason they said this is less about allocating our memory and more so that names, right, we have length of 50. So let's get into it. So looking at the return type of the function, what is the first thing that we should do? Anyone? Anyone? That emote's evil. Bro, looking evil. Okay. Actually, I should probably get the function declaration over here. Might be helpful. That is a big function. That's a big one. Okay. All right. So we have our create employees function. Is everyone saying, yeah, definitely. Let's create our first employee. So we'll get an employee pointer, and we'll call it employees, right? Because this is creating employees. So employee pointer malloc. What are we going to? What is the full thing that's going into this malloc statement? Think about size and everything else. No. Andrew's HR manager. You're forgetting something very important in the size of function. Employee times res count. That is correct. So size of employee or times emp count, right? Because we need enough room for all of the employees. So we now have our employees pointer. If we look at what the what's going on here, there's a bunch of different things inside of an employee, but keep in mind this is our array of employees. So we actually we're not really allocating anything here. What we're instead doing is we're iterating through it since this is an array of employees, right? So for an I equals 0, I is less than employee count, and then I plus plus. So now we are iterating through the employees array. What is the first thing that we are going to do once we get to an employee? So we have an employees array called employees. Actually, I'm going to go ahead and rename this res because that's actually just simpler. And I see people saying res, 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 res. I forgot the equals. I did forget the equals. Good catch. So there you go. What are we doing? What is the first line going to be? I want the whole line. Well, actually, it's kind of big. Malloc for ename. That is correct. Is it going to be res of I dot ename or res of I arrow ename? Yeah, malloc for each variable within the struct for loop is going to be dot, is going to be equal. Perfect. So it's dot ename equals, and this is going to be a string type pointer, right? So string type pointer equal, or no, malloc. Wait. Yeah, malloc.ename, malloc size of, sorry, string type. And then boom, we now have the room for the ename. Next, we're going to set result at I dot ename string equal to, and so we're basically string is going to be a character pointer, so we're going to allocate character pointer malloc, and then what is going to go inside of here? Okay, we got a few things going on here. All right. So first things first, since this is a string, we're going to get size of character. But what are we going to be multiplying that by? So we're going to first be multiplying it by the string length of, it's going to be string length of names at I plus 1. That is a long sentence. One thing I will say that I saw um, people saying is you need to make sure that you're not doing inside of string length. So, for example, you're not doing string length word plus 1. That is not going to work. It is string length of word plus 1. Keep that in mind. That will change your outcome significantly. Uh, yeah, keep that one outside. Exactly what Adam said. Way to go, Adam. Um, and then after that, so if we come over here, kind of checklist, we have the employee, their e-name is done, and their string inside of that is almost done. We first have to set res I dot ename string dot length, right? Because we have this, we can't leave this undone. I believe we need to make it. It's going to be. What do y'all think that's going to be? That's pretty straightforward. I don't know why I'm asking you guys that. It's going to be string length of names at I. And then we also have to actually, we allocated space for their name, right? We allocated space in the string, but now we actually need to copy the word over. So string copy, now that we've allocated the space for it, res of I dot ename arrow string, and then names at I. Okay, this one's a bit of a longer one. This one's a bit of a doozy, right? So we have this going on here. I forgot to close the malloc. I did forget to close the malloc. Good catch. So we now have everything populated inside of the employee's ename. Then last but not least, the final thing that we have to do is we have to do res at I dot salary equals salaries at I. And again, I'm not going to give you all that trick question because you all caught me pretty quick last time. We just go ahead and return our result pointer. So how does that look to everyone? Look good? Feeling good? Feeling fresh? So we basically went piece by piece. We made sure to get all of the different fields that have pointers. So if we go kind of checklist, employee name at ename has been mallocked. It is a pointer. And then all of the things inside of that ename, which is of type def string type, string has had memory allocated for it. We've successfully string copied over into the string. We've assigned the length properly. So ename for employee is now completely handled. The last thing that we needed to do was add the salary. So all of the fields that we need for this are completely filled out. Everything's looking good. And we can be fine and dandy on the FE. So, oh my goodness. Okay, let's move on. Right away, we are hopping straight into linked lists. So, before we even get into the stuff, the jazz behind linked lists, I wanted to kind of go over the technical reason why linked lists came to exist largely, and I personally find it quite cool. Hopefully, you all find it quite cool. The biggest thing about memory is that it is contiguous, right? And I didn't add that word into here, into this section, but this doesn't only create initialized or uninitialized memory. All of these create what's called contiguous memory. Basically, the gist of it is this. You can almost think of memory as kind of like this segment, right? And all of your values are going to take up portions of your memory. The thing with malloc and calloc and realloc and all of that is they have to have contiguous memory. So let's say this is being used by a program and this is being used by a program, right? So let's say, for instance, malloc, we wanted an array of size 4. If you look here, we have 1, 2, 3, 4, 5 open segments of memory, but a contiguous segment of 4 is not going to fit anywhere because there isn't enough room. Now, this is it really is unimportant in the context of the assignments that we're doing. But storing data this way in contiguous gets really bad when you're working with really, really large pieces of data. Even though memory is like dirt cheap, there's still kind of an issue going on here. And so basically, that's where linked lists came in. The biggest advantage of linked lists is that the memory does not need to be contiguous. You could have a linked list node here that points over here, that points over here, that points over here. And that's why linked lists are kind of, that was a big incentive behind linked lists that were kind of cool. But keep in mind, linked lists do have a lot of good memory, stuff like that. And also a very important aspect of all the other data structures we look at, stacks, queues, and even binary trees, you could think about them as just two linked list nodes, right? There are some drawbacks. So the biggest drawback to linked lists is going to be its runtime, fundamentally speaking. An array, you can access array at 10 versus a linked list, you're going to have to do a while loop 10 times going next, 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 whatever. And that's going to take you O of n, O of 10 time, right? Which is basically just O of n. Accessing an element inside of a linked list is O of n versus an array, which is you just literally do that and it is always O of 1 because of the direct access table properties of an array. So that is one of the biggest drawbacks that we have. Also, insertion at the head is O of 1 and at the tail is O of n because you have to traverse all the way down to the end unless you do some fancy stuff with end pointers, which is what we'll get into soon, if that reminds you of any data structure we've looked. And searching linearly, it's O of n. There is no binary search on a linked list effectively. So it's hard to sort of do those standard operations that you would expect with an array. However, it does solve that big issue of contiguous memory. So that is a big inspiration of linked lists. And with that being said, there are three different types of linked lists. We've mostly dealt with singly. In this case, a piece of memory, a block of memory, only points to the next node in memory. And then eventually, one distinct factor that distinguishes these two from circular is that eventually they point to null, which in this case I'm going to represent with an X. Basically saying that, hey, this is the end of the linked list. Don't bother traversing here. Don't bother accessing here, right? So singly linked lists are the ones that we are most familiar with, and some of the runtime advantage, the disadvantages of singly linked lists can actually be solved sometimes with doubly linked lists. So this is going to be represented as a line at Disney, right? We're only going one direction. Doubly linked list, as you might expect, has each node stores both the next and the previous node, which allows you, if you have that memory, you're able to traverse back and forth. Let's say you go here and then you look at the next node and it's something you don't like, you're able to just come back right here and then return this node in some sort of function, right? Like maybe we want, the node before the last node. You could like check next, but there's different reasons for all of these. Doubly linked lists have their place too, but for the most part, we mess with singly. But there have been problems on doubly linked lists before. So yeah, basically exactly what I said. Anytime you need to traverse back and forth. Circular linked lists are a bit weird. They are, in fact, circular. So they can either be doubly or singly linked lists. But the biggest thing that makes a circular linked list circular is that the next node on the tail points back to the head. Circular linked lists are a little more niche. They're not super like problems that we're kind of going over, but they're still good to be thought about. The biggest thing is kind of like a repeating schedule. I'm pretty sure like CPU schedulers or stuff like that can use some sort of like circular type of data structure. In our case, I'm not entirely sure how much we need to know this, but it'd be good to know conceptually anyways. The best way to traverse it, to my understanding, is to hold a copy of the head and then loop until the current node you're on matches the memory address for the head. If you're wondering, because I know that was a question I had that was like, huh, okay, that's neat. So yeah, since we can represent a node as a piece of data of any type and then a node pointer to the next, right? We are able to traverse linked lists like this. So basically, a linked list traversal is going to come up in almost all of the linked list problems, um, at least all of the linked list coding problems. So you need to know how to do it, and you need to know how to do it right. First thing you want to do, it's optional, but it is good practice to create a temporary node of the head's address. At that point, you're going to loop until it equals null. This is basically saying we're at end of list. So EOL, right? And then we can do whatever operation we want in this part of the code right here. But you cannot forget at the end of the loop, you need to iterate. You need to go next because there have been problems where I would do all of this complex logic in the middle and then just forget to iterate. And I'd be like, why is this not working? Why is this only ever working on the head? Because you're not you're not iterating. Like I don't know. It'll be like wow, it'll infinite loop you sometimes. So that's basically the structure. You grab a copy of the head. You while that copy is not equal to null, so this is end of list check. Do whatever operations you want, iterate to the next, and then at the very end you can do whatever you want. So in cases of like, let's say you want the sum of all linked lists or all linked list nodes that are even, you can create a running total here, right? You can create a running total, and then in the operation here, you could do a check of like, you know, if even, and then you can do, running total plus equals node data and then print the result. So it's kind of like how most of the linked list problems are. You're going to be doing some iteration. There have been problems where you actually need to iterate over two at the same time. And then really at the end of the day, it's while temp does not equal null and temp2 does not equal null or anything like that. But just keep the general structure of a traversal kind of down in your memory. Kind of get it anyways. So the two biggest linked list problem types, there's either going to be a traversal problem, which is what I was talking about, or one they also like to throw at us. That's a good test if you kind of understand, linked list, the data structure and all that, is actually a tracing function. Sometimes they'll give you a linked list and they'll say it's like 8, 3, 7, null. And then it's like call this function what it do on the linked list. And then they want you to write it after it's performed. That one obviously is a little bit of a different kind of game. But if you understand how traversal works, like this, most time you're going to be tracing some sort of traversal, right? So it'd be best, in my opinion, for these problems to draw them out. So, for example, like maybe this sets like next to next for each of them. So like it'll be like a linked list that's like this, like loops back, and you just like draw it, and then you're able to like say like okay, 8, 7, 3, just stuff like that. Um, One of the biggest mistakes for linked lists, there aren't too many, but also make sure you iterate, make sure you set temp equal to next type of thing. Um, but never forget the null check. That's like the biggest thing that they try to flip you up on is they want you to access null. That's like the biggest trick to linked list problems. But these two are pretty kind of narrowed down to a science. Don't really have to, yeah. So uh, that being said, this one is that was a pretty quick section. I'll actually give you all a vote. Do you want to do this one is coding? Do you want to do coding first or do you want to do tracing first? And while I let y'all answer that, I am going to run to the bathroom. So I'll be right back. Just give me like 2 minutes. All right, what's up, chat? What's the consensus? Let's see. See, see a lot of coding. Uh, I want both. It don't matter. Okay. Um, I'm cooked on recurrence relations. That's not today. That's not today. Okay. It looks like the common consensus. Let's get coding out of the way. Without further ado, I'll go ahead and pop this up. This is problem 2. Yeah, let's get right into it. Crazy enough, this crazy convoluted little problem here has a higher pass rate than the DMA problems. How? Silly mistakes, probably. But yeah. So let's get straight into it. Adam, the damn cat. Okay. Da, 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 um, yeah, making sure all the chat's good. Anyways, let's hop into it. So this is a linkless problem. Consider the problem of determining the number of changes in direction of a sequence of integers stored in a linked list. This feels like such a LeetCode problem. Anyways, we define a change in direction as any 3 consecutive values, A, B, and C, in the sequence where either A is greater than B and B is greater than C, or A is less than B and B is greater than C. So for example, in the sequence 3, 8, 2, 2, 5, 6, 4, 8, 3 has 4 changes in direction. So I'm going to go ahead and draw this out because this took me a second to understand too. So 3, 8, 2, 2, 5, 6, 4, 8, 3. Okay, so this series of numbers here. The first one that we're going to grab is 382. In 382, you can see a incline in the values from 3 to 8. It's going up, and then from 8 to 2, it goes down. It's basically the gist of what they're saying here. There's a direction change here. Same thing with 5, 6, 4. From 5 to 6, we're going up, and then 6 to 4, we're going down. That's a change in direction. And then you can kind of get the gist from there. 6, 4, 8. From 6, it's going down, and then from 4 to 8, it's going up. So that's basically the essence of what they're asking you here on this problem. Apparently, Ethan doesn't like this problem. Oh, this one. Dot dot dot. Yeah, this one was a little intriguing. So I'm gonna come over here. Write an iterative function that takes in a pointer to the front head of a list front and returns the number of changes of direction as defined above in the sequence of integers in the list pointed by front. Okay, so there are a few ways you can do this one. I don't need the whole struct. Get rid of that. Okay. So yeah, there are a few ways to do this one. The first one that I would like to do, just to kind of almost in the spirit of LeetCode, it's kind of like the typical thing to do. I don't want to have to deal. Why is this not? Hello? What? Okay, we don't need this last semicolon. That was crazy. The fact that they were two. Okay. Yeah, broken site. The craziest part is this isn't even their fault. This is the Excalibur embed. Okay. Um, so I want to do sort of like my guard clause. I want to make it so that there is a chance, since they told us to handle it. Note lists of size 0, 1, or 2 by definition have no changes of direction. This means that they will give us, they can give us, if we were to test this code, size 0, 1, or 2. So the first thing I want to do is I want to get rid of that case and just not do anything if we encounter it. So if that is the case, so let's go through each of them. So for a size 0, that means front equals null. That's size 0. For size 2, that means front exists, but dot next, or no, size of 1, sorry. Front next is null, right? And then last but not least, size 2, that means front exists, next exists, but front next does not exist, equals null. And that means we're just going to want to literally just get rid of that out of the bat. We're just going to return 0. Does that make sense to everyone? What I did, why I did it, and why we needed all of those nexts? No, we don't need to set A, B, and C first because we're just checking if it is length 2 at all. It wouldn't. Expand it more if I can. Yeah, my bad. This is a long little. I have Oh, okay, hold on. Let's get this out of here. Go far away. Okay. Wait, did it save all my past problems in here? No, it didn't. That would have been cool. Here. Can everyone still see this? I know it's because this is kind of like wide. It's kind of like small. You know? All right, we're all good. We're all good. All right. So basically, we're first doing our guard clause, checking if everything is true, right? So there are two ways we can do this problem. The first way, if instead of doing it all in one line, I create a variable, will it reduce my score? No, as long as the functionality is the same, your score will not be reduced for doing it a different way. There are actually two ways to do this problem. There's the way the FE actually tells you to do it, and then there's the way I did it, and both of them are correct. So there are two ways to approach this problem, and the only difference is how you do bounds. So the first way that we can do it is we can actually set up storage where we say node A equals front, node B equals either front dot next, or this is my comments, A dot next. Because in this case, that is the same thing. Since A is front, and we can say it's front dot next or A dot next. This is literally the same thing. And then same thing could be said for this. Then that equals B dot next, right? And then again, you could also, or, you know, oh wait, yeah, I'll leave it at that. I'll leave it at that. Or you could do front next next, which is personally, this isn't even the way I do it. I didn't even set up storage. I did while front and front next and front next next, but don't worry about that. I'm not going to confuse you because that was kind of like, that was kind of scuff code. So basically, while C is not null, since C is the last element, and basically if C is null, then that means we don't have three values anymore. We don't have to do anything. If instead of doing it all in line, could I do A equals front data etc and compare those values? No, you do not want to hold on to the data yet. You want to have something that you can traverse with. Because if you wanted to set A equal to the data, you'd have to do that inside of the loop because this would only declare it like in the moment, right? This is basically our trackers, just so that these are our trackers, just so that we don't have to keep writing front.next, right? So while C is not null, because if C becomes null, then like we're done. We don't have two more numbers anymore, or yeah, three numbers, right? What we're gonna do, there are two if checks here. I'm gonna kind of do it FE exam style. I'm gonna write the if statement, but I'm gonna leave it blank. I want to see what you all think are the two if statements that we need to make. Oh, and one more thing, we do need to keep our running total. We do need to keep int res equals 0. So what are these two if statements? What are the two things that we need to check for? No, you don't have to check if B is null because C will be null first. Since C is B dot next, we could think of this as if this is the linked list. The idea here is that this is C. If C, at the end, we iterate each of the pointers, each of the copy nodes over one. And so if C ends up being null, then that means that we're in a situation where B is here and A is here. If this is the case, then there aren't three numbers to do the operations on anymore. And C will become null first. That's why we're just stopping when C becomes null. Okay. I see if A is greater than B and B is less than C. If A is okay, you are close. However, no one's said it yet. There's something. There's an issue here. Yes, you need to access the node's data values. So what this is, it's not if A is less than B. It's if A data is less than B data and B data greater than C data. I think that's it. That's the if statement, right? Did I do it backwards? No, that looks right. Yeah. That looks right. And then the other one's the opposite. So A data greater than B data and B data C data. And then what do I do if these are true? Like what is the actual code that I'm executing if these two if cases are there? That means we've had a change in direction. So we're basically just doing res plus plus. And we can put that outside because it's a one-liner. All right. And if that is the case, then I can just go ahead and return res, right? Does it look good? No, it's not. What am I missing? Update. I need to iterate. So at the bottom here, we could do this whole complicated thing again where we set them to equal to each other, but you really can just do A equals A dot next, B equals B dot next. There are a bunch of different ways that you can do this problem. Another way that you could do this is you could say or A equals B and then B equals C and then C equals C dot next, right? There's a bunch of different ways you can do this. What I did is I actually put everything in a while loop. I said while front and front next and front next next. And then if it was size of this, it would just return the empty iterator after doing nothing to it. There's just a bunch of stuff. Yeah. Adam forgot to iterate. Hold on. I got something to show him. Hold on. Never. Oh wait, I didn't even add that. I wrote it. I forgot. I was gonna show you the thing that said never forget to iterate. But yeah, I think that's number array. I can get rid of this. I also realized we never went over the solution for that other problem, but I think we're fine. So ultimately, this is yeah. Does this look good? Any questions on this before we move on to the tracing? Adam, I'm rough on you because we're homies. Okay, I gotta get you up to standard. But other than that, are we all good? We feeling good? Yeah, you get it together, Adam. That's crazy. Okay. Yeah. I guess we're good and fine and dandy to move on to the next problem. No questions here, so I'll move on. The next problem is going to be a tracing problem called "What does it do?" Very creative naming scheme going on here by the FE writers. Because believe it or not, we are going to find out what it does. This is a tracing problem. In these cases, I genuinely so wholeheartedly recommend you draw out the linked list, right? So I got 3 in here. Or wait, hold on. I know what to do. Watch this. And then I'll copy this whole thing. Watch this. Y'all, I'm cooking. Ooh, we got 9, 7, 1, 4, and then null. Tell me I wasn't cooking with that copy paste thing going on. That was kind of sick. Is this a website we can use to practice with? Yes, you can go to feprep.org, plug to the feprep team again. You sign in with your NID and all that, but it has every single topic problems that you need going on here. The difficulties, what semester it came from. The only thing I would say that the feprep needs to do is adding more older problems. So you were not cooking, Dylan. What did I do? What did I do? Okay. Anyways, yeah, I asked. Okay. Back to this. Um, so we have our link list going on here. I wish those numbers were bigger. Y'all gonna have to cope. This is the best I got. So we have our link list. Let's start actually getting an idea of what this function is going to do, right? So here, right, we have a total variable that seems to be like a running total almost, right? Um, so instead of trying to figure out what it is, we could actually just honestly trace it. So the function we pass in our head. This is currently what is this? What are you talking about? What? Do y'all know how to get rid of this? That's fine. I'm gonna leave it there. So our head is currently pointing here, right? So we pass in our head pointer. Total equals 0. While head does not equal null, this is fine. Head dot data plus equals total. Okay, so this is now turning into 3 plus 0, which is really just 3. Okay, cool. And then total equals head dot data. In this case, we could also set our total variable up here at the top. So total equals 0. Then we set it to equal to head dot data. Total is now equal 3. We move forward here. Okay, so we're at 9. We're still not null. Head dot data plus equals total. So this now becomes 12. Total equals head dot data, which is now 12. So total is now 12. And we can keep continuing this process. We now can move forward, right? Now we're on 7. Seven's, this is not null. So 7 now is plus equals total, which is 19. And then total now equals, why is it copying this? Now equals 19. Move here, not null. Total plus equal, or data is plus equal to total. So 1 plus 19, so it's 20. We then update total to 20. And then we move forward one more time. Again, okay. 4 plus equals to 20 is 24. Total is now 24. And then last but not least, we iterate to null. The loop terminates. The function resolves. We do nothing. So if we call what does it do on the following list, show the list after the function finished. And again, this is our function. Does anyone here know what this function is doing? Can they put it into words? Because I believe they give you partial if you explain what the function is doing. I don't know how you could explain what it's doing without actually writing it. Like, that's kind of crazy. Adding all the previous values. Yep. This is basically called a prefix sum. But yeah, if we go to solution, 13, 12, 19, 20, 24, pointing to null. Perfect. Transforming the list to be a prefix sum version of the old list. And just like that, linked lists, we're done. Yeah, so linked lists, woo, cool stuff. But where linked lists really come into play is these next two sections. Linked lists are a data structure, but now we're going to start getting into an abstract data structure. The biggest difference is things like stacks and queues aren't much different functionally to a linked list in terms of, like, obviously if you're using a linked list implementation, or if you're using an array queue, then don't fact check me and be like, it's actually an no. A linked list based queue and a linked list based array, they're linked list based stack. They're very similar in code to a linked list, but the difference is how you actually use them. It's properties that we'll go over, but yeah, queues, because they did actually come first in the curriculum. So we'll start with queues. We are actually just following the order that most of you all were taught. So a queue. Isn't this just a linked list? Yes, it is technically just a linked list. But like I said, abstract data types, they have things that we need to do to sort of keep them as abstract data types, right? So a queue is first in, first out property. This is basically just saying that if you're going to add to, um, it's first in, first out, meaning the first thing you add to the queue is the first thing to be taken off of the queue. Think about it genuinely. I'm sure you all have heard this concept over and over again, but it's like a line, right? If this is the booth that you're getting into, someone walks into the line and they stand here. They're the first person in line. Another person walks up, they're the second, the third. But who gets to the booth first once it finally opens and the little attendant guy's here and he's all happy? The first one that got in the line gets processed, right? So that is the first in, first out, right? FIFO, whatever you want to call it. But that is what makes a queue a queue. So there's rules. There's rules on a linked list, but isn't it like a queue? It's still just a linked list. So there is a big difference between a queue and linked list when it comes to implementation. It's actually a very small difference, but it has a major impact, and you need to consider this on the FE because they love some good old runtime questions. When it comes to a linked list, we hold the pointer of the head, right? As we're working, all of the functions, they pass in head, head, whatever, right? And to get to the end of the linked list, you are going to traverse, right? You're doing your while loop, and that's going to take O of n time. But in a queue, that is very inefficient because remember, you're if you either end, right? You're dealing with both ends. So whether your implementation kind of has the front of the line being like at the end, like either way, right? Right. No matter what, you're going to have to be traversing the linked list if we only store the head. And that gets very bad because we need to be doing both in queue, which is putting them in the queue, as you can see here, and DQ operations pretty frequently. So either one of them costing O of n is very expensive. So how do we fix this? This is where queues become good, right? They're cool. I kind of enjoyed this when I had this like eureka moment in Ahmed's class when he taught this. I was like, okay, um, there is two pointers. Okay, there's a pointer to the front and there's a pointer to the back, and so now, right, we basically can do both. We are able to insert at the back of the queue because that's where you get in line. We're able to insert. We're able to end queue, right, super easily. And on that same note, we're able to take people out of the line super easily because we hold a pointer, right? So it's O of 1 to NQ, O of 1 to DQ, because we have these two pointers right here, which are typically stored in a separate struct called your queue, right? And then this is basically just, it's usually front pointer and then back pointer. And then these are just linkless nodes and another struct that we would make that I'm not going to write out because that takes a long time. Now, okay, the traversal is still O of n, but we genuinely, in most cases of a queue, we don't care about what's in the middle. We only care about what's in the front and the back. Because why would you care about what's in the middle of the queue? It's a queue, right? If we were to bother traversing to the middle of the queue, let's say we wanted to put someone in line right here, there's probably going to be a fist fight, right? We can't skip the line. We're only bothering with front and back. We're not trying to mess with what's in the middle. And so that's why this approach for queues is really nice in terms of runtime, because we don't actually really care about what's in the middle that much, and we would like to avoid fistfights. So that's basically the gist of that. And so this is what the code looks like. Mine the Geese for Geeks, but it's pretty straightforward. Basically, this is our Q pointer. Remember the Q pointer has a front pointer and a back pointer, both of which are pointing to linked list nodes. This is basically the last one, and I mean, as you might expect, the front and the back, right? So basically, we're creating our new linked list node, which is where we're going to enqueue at the rear of the line because you get in the back of the line, right? So if this is your queue, you get in the back. So we're grabbing the back of the line, rear. We're basically checking if the queue is empty, right? This is a check that you will have to make, and this is one that comes up as trick questions on linked list queue problems. Is they don't say that the list can be like that it has to be occupied, right? The issue is for a linked list, you only have to just if the linked list is empty, you just return that node, right? But keep in mind, we have to keep track, and it's critical that we keep track of these, or else our queue is not a queue, and we're losing all of our glorious runtime benefits. If it's empty, you need to set both the front and the rear to this node, right? Because a line with just by itself, the front and the back, I said that backwards, but they're still pointing to the same person in a one person queue, in a one person line at Disneyland. So you need to make sure you do this. This is one of the biggest mistakes on queue problems when it comes to linked list based queues. And then if this isn't true, then you basically say, okay, if you're at the rear, rear.next equals temp, and then rear now equals temp. So in most cases, the rear is actually on the right. So it's like this, a linked list. This is where rear is pointing. So you say, okay, this node dot next equals our fancy new node that's a circle. That's what this line does. And then q dot rear, instead of equaling here, now equals this. And we can assume that this new node k function makes next equal null. It's an init function. So now this points to null. So that's in Q. DQ is also kind of the same gist, right? We want to take someone from the front of the line, which is this side. So what we're doing is, again, if the queue is empty, there's no one to take out of it. So we're going to return null. We're not adding anyone, we're removing someone. So if there is no one, return null. Again, return nothing. Again, important, right? Other DQ functions, some of them may have a return type. If they have a return type, they're basically saying, hey, we also want you to return the data that you DQ. So basically, you'd kind of hold it in a temporary variable and then return that. But anyways, so our temporary variable is now Q front. So we're going to hold on to this node right here, right? So then this one, Q front. So this is our front pointer. Now our front points to this node instead. So we've lost access to this node in our Q pointer, but we're holding on to it in the temp variable right here. And then we're basically saying, okay, if we make it so that it becomes an empty, right? So front becomes null. So like if this was the last thing in there, we need to make sure that we set Q of rear equal to null as well, because again, we need to make sure that we keep this intact. That's very important. And then last but not least, we free temp. In chat, why did we not free temp as soon as we grabbed it? Okay. Y'all cooking. You lose the rest of the queue. We lose access to it. Yep. And it would also be a use after free, because this is basically equaling this memory, right? And if we freed this, then we also we're freeing temp, but temp points to this memory. So this would actually free Q front as well. And then we would be accessing freed memory. Use after free. Big no. Right? None of that. Can't be having none of that here. Yeah. So beyond just losing the data and having a memory leak, that is a use after free. Not good in the slightest. Okay. Array-based queues. Personally, I'm not a big fan. I'm not going to lie. But doesn't mean we don't need to know them. So we are able to represent a queue in an array. How do we do that? Well, I hate these. I love these. That's crazy. The biggest difference is, oh, he's lying. Well, then that makes none of us, I guess. Yeah, you can represent a queue with an array and a bunch of fancy numbers that you can keep track of to keep everything, intact. So the things that we need to know is we need to know number of elements, which is the number currently in the queue. We need to know size, which is the actual size of the array. So in this case, number of elements would be 1, 2, 3, 4, 5, 6. And size would be 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? It's important for our checks if it's full or not. And we also need to know front. And other than that, and obviously we need to know the array itself. And this is basically what be stored in a array-based queue struct. And that's pretty much it. How do we do it? Well, okay. So we want to add something into the queue. Well, we're going to first make an if check. If number of elements is less than size, that's the only time we can do it. If not, return. This is our guard clause, right? This is making sure that we don't try to add something to an array that's already full or accidentally override data. Like, for example, in this case, if it were full, say there's like 1 here, and then we add to it, we would take 10, and then we would kill it with our new number 2. That's bad. So we don't want to do that. Instead, we just want to say, hey, the queue's full. So basically, what we do instead is, let's say this is the front. So in this case, right, our number of elements is 6, our size is 8. Let's say we want to add a number to this queue. Let's say we want to enqueue something. So we're going to enqueue it at front plus number of elements, which is front is at 0, 1, 2, 3, 4, 5, 6, and we can enqueue 1 right here. But we need to remember to mod size. Can anyone tell me why we need to do that operation? Circular logic to wrap around. Exactly. So for example, if this was already here and size was 7, is a bad example actually because we don't have an offset. Okay, y'all get it. And then make sure you need to increment number of elements afterwards. So the number of elements is 7. Boom. We now have enqueue, right? Instead of doing this, it's kind of the same thing. It's nothing too crazy, right? DQ. First thing you're going to do when you decrement is you are going to get rid of the number element. You're going to decrement it by 1, right? You're going to, so like, let's say we wanted to DQ, say we wanted to DQ 15 in this array. 1, 2, 3, 4, 5, 6. Number of elements is 6. Size is still 8. And front is 0. Okay, so we're going to hold on to the data in array of front. In this case is 15. So we're holding on to 15 in a temp variable here. After we decremented number of elements, the number of elements is now 5. And now front is basically just front plus 1. And you have to remember to mod size, because in the case that the next area, front plus 1 is here, again, mod size to bring you back over here. This is the new front. And then basically you just return 15 if they have a return type and they want the data that you're dequeuing. And yeah, are we going to be able to access the videos after? Yes, it is recorded. This will be on a Zoom meeting. It takes, I'm not gonna lie, it takes like an hour for them to index all the transcripts, but as soon as it's done, assuming I'm not busy, I'll go ahead and publish it. And I might publish the slides too. I probably will publish the slides too. I'll just publish the slides that we went over today. That'll be kind of easier. So, okay. Yeah. So there you go. We got queue problems. Unfortunately, there was not a single array-based queue problem on FE Prep, so I had to go into the dumps and pull out a foundation exam pass problem. So since last time I asked, y'all gave me sass about getting you free will. We're just gonna go ahead and start with that front. I'm pretty sure it was only one person that gave me sass, but we're back in like pre-K and it's like one bad apple, you know. Yeah. So too bad, Adam. Here we go. We have I'll zoom it in one. It's fine. We have what problem is this? It's 3. Yeah, this is our normal queue linked list problem that's goaded and not an array-based linked list. Joey just did this one. Sorry, you're gonna have to go through it again with the rest of us. Man, FE Prep, I really wish this was draggable. All I'm saying is loot code's draggable. I'm self-plugging real quick. Yeah, so a regular queue only supports adding an item to the back/tail of the queue and removing the item at the front head of the queue. Okay. A common method of implementing a queue is a linked list with pointers to the front/head and back/tail of this linked list. A common method of implementing, whoopsie daisies. If the method is used, it's relatively easy to add the functionality of adding an item to the front head of the queue and removing an item from the back tail of the queue. Given below is a partial implementation of this data structure, commonly called a deck, also known as a double-ended queue, so that you're able to basically add and remove from both ends of the queue, at which point you're just like, this is basically just a linked list with a head and tail pointer. You'd be right. Fill in the function that adds an item to the front head of the queue. You may call the make node function, and you may assume that my deck points to a deck that exists, though it may or may not be empty. This is a glaring clue that they want you to make those null checks I mentioned that always trips everyone up. Also, yeah, I say deck. You could say deque. You could say, I don't know, bro. Look at it. It's like deque. I don't know. I don't. You got to tell me what you call it, but I'm calling it a deck. Read in chat. Yap. Okay. Deck is better so you don't get confused with DQ. Yeah, that's a good point. That's a good point. All right. So I'm gonna go ahead and get the function declaration kind of pop in here. Did it do the same thing again? Where this is by? Why does it do this? Why is this by itself? Okay, I'm leaving it. Goodbye. So we have our add front function. So let's go over really quickly what this actually like wants us to do. It wants us to add to the front of a queue. So basically, it wants us to access my deck at front and then add an item to there, right? Even though realistically, we normally add to rear. Okay, this doesn't sound that bad. This sounds just like a linked list problem masquerading as a queue problem, right? Well, the first thing that we're going to need to do is we're going to create a temporary node of this value. We're assuming that make node, and actually they give us the code. Make node goes ahead and creates a node that points to null and everything. Like everything's safe, everything looks good, so we can just kind of use that. And also a deck, it's a double-ended queue. Literally, it's a queue, but the abstract thing of like first in first out isn't real. You can add and dequeue from either side of the queue. It's literally just a linked list, but you have the 2 pointers to front and end this time. It's weird. I honestly don't know why they did it. What if for linked list we just stored a pointer to every single node? That'd be kind of crazy. Anyways, yeah. So we first have to make the temp variable or the temp node. So we call it with make node. It returns everything's nice. What is conceptually? You don't have to write the code. What we need to do right now before we start doing any sort of processing? Check null. Check if front is null. Okay, so if my deck at front equals null, then what? What do we have to do if the front equals null? It says assume the deck exists, but it may or may not be empty. So what this means is the deck pointer exists, so we don't have to check if my deck is null, but we still have to check the stuff inside of that pointer. Yeah, so set front and tail to new node. So very simply, we could just do my deck front equals my deck rear back equals temp, and then return. You are also completely able to just do that in 2 separate lines. My deck front equals temp, my deck back equals temp. That is perfectly fine. That's fine. And then, yeah, after that, now what we need to do? It's kind of 2 things we need to do. What's the first line? What do y'all think? That is correct, Joey. Temp next equals my deck front. And then after that, there's one more thing we got to do. And then front equals temp. Boom. And if we go here to the solution, almost verbatim, we go ahead, we create a temporary node. If the deck front is null, we set them. Look, I did it different, guys. I'm cooler. I did it the hip way. And then we set temp next. It was my deck front. And then boom. Does anyone have any questions with this and why we did that? Do not be afraid to ask. Anyone going once? It's giving me a good stretch break. What does the last 2 lines do? Okay. So if we're considering a queue where we have, let's say, 3 elements, right? Ooh, right there. And then I'm going to do the same copy strategy again. So we set this here and then set this here. And then this points to null. We also have a pointer That's our front pointer here, and oh, what the heck? What? I could do that? How do I stop? Okay. Anyways, and we also have our rear pointer here. So we have front, and we have back. We're adding to the front of the line, and so it's basically just an NQ function. Yeah, pretty much. So we have a temporary node here that we're trying to add to this side, to the front of the list or of the queue, right? So what we do is we say temp.next. Can I bend this again? No, it's gonna let me do the weird thing where I like yeah. Okay, hold on. Okay. So temp.next is equal to my deck front, which is pointing, it's actually equal to this, which is pointing to this, right? So I'm just simplifying it. And then we say my deck front now equals temp, right? Move this, it's pointing here. So really when you simplify it, it's basically just doing this. It's just adding to the front of the queue. And see? And now it's the exact same queue except we added this temp node to the front. Did that answer your question? Got it. Perfect. Cool. Oh, okay. Getting a good stretch in. All right. On to the next one. I'm going to have to go ahead and open this all up. I think this is the solutions area. No, we don't want that. And then here it is. As you can see, third problem, always the queue or stack problem. It's like exact. Unfortunately, I'm not going to have my my drawing. Actually, Excalibur got me, right? All right. Am I able to I just took a screenshot of my whole screen. There you go. I should be able to just go to like normal Excalibur. Got a bunch of other stuff going on here. Okay, cool. All right, so this is our array-based queue problem. Or use paint. Okay. Where's my dark mode at? Do I have to pay for dark mode, chat? This is crazy. Haha. Okay. So I don't know why it's not using system. Cool. Suppose we wish to implement a queue using an array. So literally just an array-based queue. The structure of the queue is shown below. If you remember, the notes don't save. This is exactly what I said. Number of elements, front. In this case, instead of size, it is capacity. And then, yep, array. Good old stuff. The num elements is size. No, num elements is the number of elements currently in the queue. Capacity is the actual maximum that you can have. So like the length of the array, num elements is the size. Yeah. So the queue contains the array and 3 attributes. The current number of elements in the array is basically saying right here, the current front of the queue and the maximum capacity. Elements may be added to the queue, not just at the end of the array, but also in the indices at the beginning of the array before front. Such a queue is called a circular queue. This is basically just saying a bunch of yapping for mod size, right? We can add anywhere, right? Saying that you can add before the front in terms of indices because it wraps around. Write a function to implement the dequeue functionality for the queue while ensuring that no null pointer error occurs. Your function should take in one parameter, a pointer to the queue. Your function should return the integer that was dequeued. Okay, so like I said, there's some specification with dequeuing. You can be requested to return the actual thing that you're dequeuing. If queue is null, or if there are no elements to dequeue, your function should return 0. So we have whoa, it copied it from the other Excalibur. Okay, that's kind of hype. Struct. I get excited over the weirdest things. Q and then bam. Okay, so first thing we are going to do, since they basically said that we can get a null queue or no elements in the queue, I'm just going to go ahead and knock out my guard clauses real quick. If q equals null, so if the buck, if q equals null, we return 0 as the problem specifies. I'm just going to do that in line. right? Save some space. And then again, if we have no elements to DQ, then how can we check if there are no how can we check if there are no elements in the queue? What is like an if statement we can make? Yep. If q num elements equals 0, then again we return 0. So here we have our little kind of right off the bat, getting things nice and prepped for what we're going to be doing moving forward. And then from there, we do, first thing we want to do is we want to hold on to the value because we need to return it, right? So that's what I'd like to do first. So we can say int result equals, what are we returning? Bro didn't do it the cool way. Okay, so we want Q array at front. Okay, cool. Q array at Q front. We grab the element before we do anything to it, and this is what we're dequeuing because we dequeue from the front of the line. We then want to go ahead and update everything. So Q front equals, what does Q front equal? Everybody? Next. Q next. No, that is not Q next. Keep in mind that we are working with an array-based queue. We are not using a linked list queue. We need to use our array access methods. There is no next operator because these aren't nodes. So, yeah, nice typo, Joey. You're clowning on me. Can't even spell it right. So Q front is going to be Q front plus 1. Is that what it's going to be? Percentage dice. Okay. And yeah, we do want to mod. That's an ampersand. We want to mod by Q capacity because there is no size variable here. Make sure you make your variable names right or they will dock points. Is that it? We can go down here and return result. Decrease. Yep. We need to go here. We need to do Q num elements minus. Okay, am I base for using minus, not minus equals, guys? Yeah, and so if we come here, we should be able to go to our results and then come down here. Is this even the right? Yeah, okay. So we basically check if Q is null. Okay, we got that. Okay, we got that. Guys, just the guard clauses, just the 2 null checks is 3 out of 10 points. Crazy talk. Why did I just copy it? Anyways, you got those 2 down. Holding on to the value and then also returning the value is also 2 points. You could get half credit without actually doing the DQ. And then you basically do this. Q front equals Q front plus 1 mod capacity, and then Q number of elements minus. And that's about, does it matter where we increment? No, you could honestly increment. Well, you have to do it after the guard clauses. You could increment at the decrement at the top. As long as you're not accessing this after you decrement it, it doesn't matter where you put it. So that's the only thing. You can't put it before your guard clauses. So as long as it is after the if statement. Yeah. So that we got 2 more sections left. And I don't know about y'all, but the stacks aren't too bad. But explaining recursion is going to be a doozy. Okay. Let me get a little stretch in. All right. Okay, I'm ready. I'm locked and loaded. Stacks should be free points, realistically. Infix to postfix should be free points. However, I will say as a disclaimer that there has been a postfix infix problem for the last 3 years. So don't take my word for it, but I don't know if we're going to see one this exam, which is kind of lame because personally I would appreciate one. Study both equally, Uh, and if somehow after me telling you not to take my word, you still take my word and only study Q's and its stack problems, I'm not liable for your failing grade. Have some free will, as Adam enjoys. So he's just gonna go straight into it. I'm only studying recursive coding. So I'm cooked. No, no, you're not cooked because look, we did the Q problem a second ago. It's not that bad. Woohoo, Q's. Okay, so stacks. Ignoring the whole infix postfix debacle for now. We're just talking about stacks. Um, they're basically again an abstract data type because they can be represented as linked lists or arrays. What makes a stack is the property that last in first out. So instead of you getting into the line and being the next out, whoever just was like the last element put in is the first one coming out. The best way to think about it, believe it or not, is a stack of plates where you place a plate on top of this one and on top of this one, top of this one, on top of this one. And if you want to grab a plate, you grab this plate. And so this was the first in. This was the last in. And which one comes out first? Well, the last in, first out. Crazy, guys. Last in, first out. So stacks are really cool because there's some interesting stuff that's going on. Also, algorithm analysis is going to be tomorrow. We are going to try our best. It is a complicated subject, but yeah, that's tomorrow. So we got this. Yeah. So push. That is basically the stacks version of NQ. We're putting something onto the stack. Again, this is O of 1. Pop. This is DQ. Take something off the top of the stack. And some of the applications, as you might know, is infix postfix. Obviously, stacks come up in backtracking a lot with some more like dynamic programming, like recursive heavy stuff. Stacks can be involved with. Function calls are also put on a stack. So the last function that gets called, so like this function calls this function, once this resolves, it goes off the function stack and it goes back up. So like in a recursive tree, this is your first one, second one, third one. This is your third function that goes into the function stack. It's the first one that resolves and goes out. So stacks are used there. Syntax parsing and valid parentheses, these are one and the same. So for example, determining if this is a valid parentheses, you can actually use a stack to do this. Through a bunch of fancy smanchy stuff. I think we did have to do that in a lab one time. But yeah, that's basically stacks. But that's not like the actual big thing going on. Most of the stack problems we get are infix postfix, but still, array-based stack. It is the most common implementation of a stack because it's just that damn easy. Pushing is top plus 1. Again, you also need to make the check if number of elements less than capacity, right? But still, stack is top plus 1. Increment the top. To get the item, it's at the top, and then decrement, and then return the item. That one's a lot simpler than all of that. Could they give a coding postfix infix question? No, they will not give a coding. You will not have to code a full program. So that's why ultimately I think that's why stacks are almost always infix postfix problems because all of the all of the code you could do with stacks get really complicated. Like the most simple thing they could give us is a parentheses checker, and even that is a little tough for a foundation exam in the time that we have. Yeah, we would need 2 hours just for the infix postfix coding. It's a mess. The parentheses one I could teach, but I don't think they'd hand us a parentheses one. And I think we are getting near the end on time. If we have time left over, I could show the parentheses one, but it's chill. Sometimes with stacks, they will provide a bunch of helper functions and just do the logic. That works. Yeah, peek and push. By the way, peek is just returning the element at the top, just looking at it, and they'll describe what peek does in the case that you get some sort of problem like that. Wait, what? I got the same slide twice. Okay, well, ignore that. Infix postfix. So basically, this is a very, very, very popular question, and it's typically 10 points. So it'd be good to know it. Although My prediction is that we won't see one, but I would very much like to. Basically, infix is how we're used to. It is just normal old, uh, arithmetic. The concept of postfix is that the operators come after. So, for example, we have 4 times 2. That turns into 4 2 times. And then whatever this result is, we add 3 to it, right? But in this case, since the operators post the number, that actually becomes 3 plus. And then again, we add 8. So it's actually, but because of order of operations, a bunch of stuff, right? We'll go over. Why do you think we wouldn't? It is just personal opinion, but there have been like if you go back and look at the past foundation exams and go to the stack Q problem that they give us, it has been stacks infix postfix for a while. Personally, I would think that they give some sort of variation after. I think it's been 3 or 4 consecutive exams that have given us a postfix problem. We haven't seen Qs in a bit, so I'm thinking that they might switch it up. But again, that's just me vibe checking this exam, and I do hope they give it to us anyways because they're nice. But yeah, okay. So going into infix postfix, really, this is kind of hard to fit into like it's kind of it was a little difficult to describe. So I need you all to bear with me. And again, if you have questions, it's okay to stop me where I'm at and just ask me the questions. I'm okay with that. So basically, this can be represented as a stack. There are actually technically 2 stacks, but I don't really count the other as a stack. There's actually the postfix expression. This is actually what we're getting from all of this operations that we're doing, right? All of this jazz. Um, Apparently, this is a stack. I just kind of think it is a string or like a result. But then there's also the op stack, which is where you're putting all of your operators. This can be represented as a vertical stack with lines. And most of the problems, as you will see when we go over it, will have you represent it this way. They will ask you what the stack looks like at certain points in the operation. So, for example, they would like you to show what the stack looks like at point A and at point B. Don't ask why C is back here, but at point C, right? So you need to get used to representing it that way because that is how the problems will ask you. So basically, the way that I've kind of narrowed it down, I've tried narrowing it down to 3 steps. Traverse the infix expression from left to right. Operands, which are the numbers or letters, go directly to the postfix, right? So in the case of this problem, I'll get to that in a sec because we actually have a parenthesis right at the start. We add operators onto the stack. If the item that is going in, so like for example, in this case, we'll have a star, we'll have a multiplication, and a plus about to get put on top. If the item you are adding, this one, not this one, if the item being put on top of it is lesser or equal priority than the top of the stack, keep popping the items until until you can place the item. So actually the better case would be, here, let's make it like star minus, right? So we're attempting to place this on top of a star. The best way that I think of this, because the simple rules you can try to remember, but sometimes I forget. If you're trying to think about order of operations in the way that you do them, right? Since multiplication always comes first, like when you're evaluating without parentheses, obviously. If we were to put this plus on top, then when we pop everything out at the end, the plus will come down to the postfix before the multiplication does. And that is wrong. So what you want to do is you see the plus, we're about to place it on top of a multiplication. So let's go ahead and put the multiplication down. Then the subtraction operation, remember, it's lesser or equal priority. So we do another pop. The minus comes down. This is gone, right? Another star, pop it out. And then now the stack is literally just the plus. Okay. So that's my rule of thumb. The way I think about it is you want to basically have like if you're placing something on top of it, it would ruin the order of operations because when we pop everything off at the end, the plus will go down before the multiplication goes down, and that's wrong, right? So this is how you handle operands. The question of parentheses, which is what threw me off because I missed this entire week of lectures. They were explaining to me by having priority 0. That didn't really make sense to me. The way that I'm personally going to describe it is that for parentheses, you basically don't bother until they close, right? So in the case of this, let me go ahead and show you. So the first operator we hit is an open parentheses. We hit a plus, we hit a star. We can place this on top because the item we're placing is not of lesser or it's greater than the top of the stack, right? And then we hit, or well, actually, there's a parentheses here, and then the star, and then close parentheses. Whenever you hit, once a parentheses is closed, get rid of the parentheses, and then stack or pop everything in between. So this multiplication would come down, and this would be empty, right? Parentheses are not in the resulting postfix expression. Parentheses do not exist in the postfix. With that being said, in the event that you have something like this, where you have, okay, I'm trying to think about the best example to do this. Let's say you have an open parentheses and you have minus star star. If we are adding a subtraction operator here, right? This is less than, or it's less than the star. So we pop the star. The star is out, the multiplication operator. Same thing with the minus. We pop the minus out because they're of equal priority. Once we hit this parentheses, we stop the popping. We almost treat the things between two parentheses as its own separate stack. We place the minus here. What we will not do is pop the parentheses because we know that there's a star under here. We don't break that. The parentheses are almost a mini stack, right? So you want all of those. So when you hit that encounter where you need to pop in order to place it, you don't pop past the parentheses. The parentheses stay there. So that's basically it. Step 1, operands go straight into the postfix. Step 2, add operators into the stack, popping when the thing added is of lesser or equal to the thing at the top of the stack. Parentheses, treat parentheses as their own little mini stack, never pop past an opening parentheses. And then once that parentheses closes, pop everything in between them in order. That is basically the general gist of infix to postfix. Any questions before I move on to postfix to evaluation? Looking like no questions. Final call, anyone? Smiley face. Hell yeah. Makes me happy to hear. Moving on. So now we have postfix to value. This one is significantly easier, but has one little simple mistake that you can make, and that is order of operations. So, okay. All right, Adam. All right, funny guy. He's mad now. Basically, you have a postfix, right? So let's say we have I don't know. Let's go get this postfix. That's kind of bad because they're letters. I'll do 1, 2, 3 times 4, 5 minus divide plus. This is going to be an ugly number because there's a division operation in there, but it's fine. We'll simplify. Okay. So basically from left to right, per usual, we're going to take everything, not just operands or operators, everything, and we're going to put them into the infix, the postfix, or whatever you want to call it, bro. The stack. Here we go. So I'll go ahead and create the stack. What you want to do is add numbers. And then once you encounter an operand, so we have 1, 2, 3. Once you encounter an operand, you grab the top 2 elements from the stack. But you need to remember this. The top is B and the bottom is A. Now that's fine and dandy, and actually doesn't matter at all if you're doing multiplication or addition because we know they're commutative. So basically, 3 times 2 is the same as 2 times 3, right? You evaluate it and put the result back onto the stack, okay? And you keep doing that. So we took those two off, we did the multiplication. Now we're at 4, 5, minus, right? So in this case, B, A. What are we pushing back onto the stack after we evaluate this? What number is going back? No. You do A first, so the number, then operand, then B. So 4 minus 5. We're putting -1 back onto the stack, right? And so basically you always do A, I'll just do a circle for operand, and then B. So in the event we get to this division operator, I think that's going to be -1 is B, 6 is A. So it's actually going to be 6 over -1. That's the difference between having a -6 put back on the stack or -1 over 6. You need to remember that the top of the stack is B. It is A operator B. You need to remember that. And see, if you even look here, again, it's easy to forget because with multiplication, it doesn't matter. 2 times 3 is the same as 3 times 2. Same thing with addition. 1 plus 2 is the same as 2 plus 1. But for subtraction and division, you need to make sure, that's the biggest fault that people have with this, you need to make sure that B comes where it belongs, right? A comes first, operator, and then B. Right? So all of that jazz. And how does it know it's -1 and not 6 minus 1 when you place it back? Expand on that. I don't understand the question. How does it know it's -1 and not 6 minus 1? This is a bad drawing. It's because you evaluate, because I ran out of room. So it'd be better if we pull it up here. So we could do like 1, 2, 3 times minus 4, 5, and then anything it was right. So the way it works is the stack, we put 1, and then we put 2, then we put 3, right? We're iterating through. So now we're here. We encounter this multiplication operator. So we add the multiplication to the top. Once you hit an operator, you pop off A. So this is, okay, this is A, B, operator. So you pop everything off and then do A, operator, B, which in this case is 2 times 3. This equals 6. Once you have the result, you push the result back onto the stack. So this is now what it is. Because the first number you have is 1, then 6, but you placed back as a result, and finally the -1. Yeah. So we have this now, right? We add 4 on top. We add 5 on top. We hit a subtraction operator. So again, this is operator. This is B. This is A. So this comes out as 4 minus 5, which equals -1. And again, we take everything off the top. We get -1 at the top of the stack. Okay? So we're back. Everything looks good there. Our thing is now over. We did 5 minus. We're here now. How do you know whether you're putting operators onto the stack or the numbers onto the stack? So whenever you hit an operator, you basically pop the operator and the top two numbers off of the stack, and then you put the result back onto it. So you go from left to right. So we put 1, we put 2, we put 3. We have an operator. So now the stack, we pop this off, and this off, and then push the result back on. That's where 6 came from. Oh yeah, okay, it depends if they're infix or postfix. They will tell you. So like Yeah, this is from postfix to value, right? This is usually a smaller question. These are usually 5 points. This operation right here, this longer one that I was talking about, this one is usually 10 points. So that's how you know. It'll say in the question, it'll so like for example, for problems with this, they will have the answer will be this. Why is it not giving me my? The answer will look like this, and they'll say fill in every value of the postfix. So in this case, it would be A, B, C, star, D, E, etc. from this, because this is the postfix, right? This is what the answer would be, and it would have the exact number of spaces you need. For this problem, it would literally give you the infix or the postfix. It would be like A, B, C, D, star, divide, minus, and the answer will be this. So that's how you know which one you go off of. Yeah. So from infix to postfix, the stacks get all the operands and the numbers come straight down. In postfix, it's not postfix to infix, it's postfix to value. But from postfix to value, you basically just get everything goes onto the stack, and you just procedurally pop things off whenever you hit an operator. So both things end up making it to the stack. Did that answer both of your questions? Yes, thank you. Perfect. So that being said, we can now run through one of these problems live with an infix to postfix problem. So we're basically going to go step by step here. So since, again, this is coming here, we have this big thing. This is basically saying, hey, we're going from infix to postfix. We want that really long expression that you've made, right? That's like, we need that. So, of course, if we want the credit, we're just going to have to give it to them. So first things first, on these problems, just by the way that like the way I like to bookkeep myself is the biggest thing that one of the things that they want is they want the state of the stack at these different points in time, right? So really quickly, I'm gonna write here a. Why is it tabbing this forward? Should be better if I just B C so that we can keep track. But then what I do on this problem is I'll draw my stack here until A, and then when they want A, I'll plug it in here like a little screenshot and then continue drawing my stack here as I go on. And then B, I put it in here, and then I continue drawing my stack here, drawing things out, moving things around. And then on C, I give them a little screenshot and then do this as I go, right? So, and then I'm also going to get the postfix down here. So by rule, the way everything goes, and then I'll have our actual stack here. Okay. Does this look good? Is everyone getting where I'm going with this? I hope this is fine because this is kind of hard to do with text, but we're going to make it work. So from left to right, we have 3. 3 is an operand, so it comes straight into the postfix. I'm separating these with I'm trying to think about the best way to separate them. I'm going to separate them. No. You'll see the space, okay? Because I was trying to make bars, but whatever, right? So we hit 3. We hit an operator. We're putting it into our stack. Our stack now has a plus in it. We're back down here. We hit a 1. That is an operator or operand, goes into the postfix. We hit a minus. Now, what happens here? We're trying to place minus into the stack. What happens? The pipe key looked too much like 1, Rob. Okay. So we pop the plus because it is of lesser or is of the same priority. So the plus has been popped and it moves down to the postfix. Okay, cool. We are now on the minus. We hit a 7, so we'll bring that down to the postfix. We hit an open parentheses. So we're going to put this into our stack. That is important. It's not going to do anything though, not yet. We're going to go ahead and hit that 4. 4 comes in. Division operator, that goes in. 2, back over here. But one thing. What's it called? Before we hit the Wait, I missed something. I also forgot after the 7, I forgot the star. Yeah, I skipped the multiplication. So like 7 star. This is what our stack looks like after we do this, okay? So they specify that A indicates the expression after the multiplication. So like after this one. So our stack is where A wants it. So now in A, I'm going to come over here, take my little screenshot. Boom. Now I can keep going. So we hit the multiplication. I didn't forget it this time like an idiot. We hit open parentheses. We hit 4. I already brought it down. We hit division. And we hit 2. I already brought the 2 down. We hit plus. What happens now? Do we keep the plus or do we have to do some popping? Pop. Okay. We don't pop the plus. We pop what's already in the stack until we're appropriately able to put the plus. So now the division comes out after the 2. We now have our division. Okay. So we're here, right here. We now bring down the 5. Since we're here in the stack and we have hit a closed parentheses, everything that's in between the parentheses gets popped, in which this case is only the plus. So I'm going to bring the plus down after the 5. Okay, we're all done there. We have a multiplication. What happens with that multiplication? What's going to happen is we place it on top of the stack. We're going to pop what's already in there. This is okay. This relationship right here is fine. We can have the multiplication above, but I'm going to go ahead and bring this down. Okay, now we hit an 8. That goes into the postfix. We hit a minus. That goes into the stack. This is not allowed, right? We have the minus over the star. So we're going to pop this out. And we still have to pop this out too because they're same priority. So after the 8, we're getting rid of a multiplication and a minus. The stack now looks like this at this point. So we now have a 7 right here. Bring the 7 down. We have a division operator right here. This is okay. The higher priority is on top. This is fine. Everything's okay. We then have an open parentheses again. We have 5. Comes down because operands always come down. We have a minus. This is okay to be put in here, but at this point we've hit B. So let's go ahead and take our little screenshot of what B would look like. Okay. Now we have a 3. We're going to bring the 3 down. We have a plus. Once this plus is on top of this minus, what happens? Are we popping the minus, or are we good to put them on? Pop minus. Perfect. So we'll pop the minus. Minus comes on down. And as you can see, this is a pretty tedious process. We hit the 5, the minus. Oh yeah, the plus. Okay, so we're here now. Another open parentheses. So we actually, after that plus, hold on, I kind of lost for track where I'm at. 5. Then the minus came on. We popped that out. Yeah. 3. Yeah, we're at the open parentheses right now. Yep. Open parentheses. We bring the next 5 down because there's another 5 here. And then we add the plus. This is okay because it's in a parentheses by itself. We close this parentheses, right? So now this plus gets popped out. Now we add the divide on top, which is okay. That's allowed. And at this point, we've hit C. So we're going to go ahead and take our screenshot of C stack. And then open parentheses. 3 times 2. Oh, that 3 is a hashtag. 2 comes down here. Close parentheses gets put onto here, right? So now we pop the star. and then another closed parentheses, which means now we pop everything in between them. So divide and plus. And then after all of these are popped, once we finish the end of the expression, we just pop everything off that's remaining. Like we get rid of everything else. So then divide minus. Okay. Yep, I'm going to show the whole postfix expression, and I'm going to show it with our solution. So stack it A, multiplication, subtraction, good. B is subtraction, parentheses, division, subtraction, and then division, addition, parentheses, yeah, all of this, right? We have 3, 1, plus 7, 4, 2, divide 5, plus times 8, times minus 7, 5, 3, minus 5. I forgot to bring down to 7, but everything else is ordered, so that's what matters. Plus 3, 2, times divide, plus divide, minus. And so boom, we get 2 points for each stack, as well as 4 points for the total expression with partials. If you get this question, you're cooking. Absolutely. This is a very like straightforward problem, but there are places to mess up, so don't be overconfident. But yeah, that is that. Carrying on to the postfix to value. This one's a lot quicker, a lot simpler. Okay, so same type of deal going on here. We're gonna have our two stacks. We're gonna have A, we're gonna have B, we're gonna have C. We're gonna have our actual stack, and then we only have one value, so this will be easier because I'm not drawing all over everything. Will they ask postfix to infix? No, they will not ask postfix to infix. They will ask postfix to evaluation, which is what we're doing right now. But no, they won't. They won't ask that because I'm pretty sure the way you solve that isn't even with a stack. So that's kind of stupid. Okay, so again, just refresher left to right. We put operands until we hit an operator, at which it goes operator BA. We perform A operator B, and then put the result back onto the stack. So to get started, we have 4, then we have 3, we have plus. So we have to do 4 plus 3, which we already know is 7. I don't need to do any fancy math there. The stack is now 7 because we did it and then put it back onto the stack. They asked both. That's crazy. They asked postfix to infix before. Damn, that's tough. I mean, you should be able to like. No. That Yusuf, that's not postfix to infix. That's postfix to evaluation. To a value. That infix is the original expression. That's what I'm doing right now. Yeah. They still have it? That's crazy. Anyways, so we have 7. We put 4, 3, and plus. We did that and put it back on. 7. Put 5 on top of the stack. Put 2 on top of the stack. We now have a minus operator. So we're going to take these out and replace it with 5 minus 2. So we take this out. 5 minus 2 is 3. So now this is what the stack looks like. We hit a multiplication operator. So that's 7 times 3. It's 21. We put 8 on the stack. We put 7 on the stack, at which point we can take a screenshot for A, because that is what A is looking for. We can continue to move on. We add 9 onto the stack. We have a plus operator. So we're going to pop everything and return it with 9 plus 7. Sorry, y'all, I just sneezed. Okay. I forgot where I was at. That sneeze is wicked. Okay, we were at this plus operator. We have another plus operator, right? So now we have 16 plus 8. That is 24. We hit 6, put 6 on top of the stack, and then again, at this point, we have 6. So we can go over here, put 6, put the state of the stack. We have a divide operator. This, again, is going to be 24 over 6, which is, oh my god, 4. Yeah. I'm cooking. 4. We put the 9 on top, 4 on top. You get a minus, which is 9 minus 4, so that's 5. We have another, we have multiplication, which is 5 times 4, or 4 times 5 technically, but it doesn't matter, which is 20. And then the final minus operator, which is going to be 21 minus 20. And that final expression is going to be 1. And so there you go. The value is 1. So we had a solution, 7, 8, 21, 6, 24, 21. Oh, I forgot to take a screenshot of the stack, but y'all saw it. Y'all can fact check me. Y'all, yeah, we did forget C. Listen, guys, listen. Y'all saw it. You can rewind the video once it gets indexed. So we cooking. And then the value is 1. 1 point for each stack, all or nothing. 2 points for the final answer, all or nothing. There isn't much partial here, so if we somehow get one of these, don't mess up. That's all I'm gonna say. All right. Yeah, this is the last section for today. And my goodness, am I tired. Y'all a piece of work. So our last topic's recursion. Yeah, I'm gonna run to the bathroom again. I'm drinking a lot. I gotta keep my voice fresh, so I'll be right back. I would never drink on the job. It is water, dihydrogen monoxide. It's the good stuff. Y'all gotta stay hydrated. Okay, so recursion. This one is hard. It was kind of hard to describe, but I tried to do my best. So, give me some leverage, I guess. In the Ahmed faction, I included a silly little meme. I hope you guys find it enjoyable. Um, so recursion, right? Big old scary monster. We use it all throughout the curriculum moving forward in binary search trees, in heaps, in tries, and all of the different type of like data structures we're doing. So it's important, and that's why we're learning it now, because we kind of need to get a little bit of a grasp of it before we get on to the hard stuff. And also, we do you can use this for linked lists as well. It's something I forgot to mention. And yes, it does recur. Okay, it recurs. The biggest thing to identify recursion is a function calling itself. Pretty straightforward explanation, if you ask me. You have a function called func, and in func it calls func. Boom. Recursion 101. You've now written a recursive function. Will it run forever? Probably. Not probably, definitely. Will your function stack blow up? Yes. In which point, Stack Overflow, who's currently being bought by OpenAI, I'm pretty sure, which is kind of crazy, like tech drama, but whatever. This is the best way you can kind of identify recursion, but by no means does this make a recursive function proper. It's just kind of like, okay, this kind of like idea is here, and right, this is an infinitely recursive loop, because this image, the image for this one calls itself, and then yeah, in case you didn't know, guys, it recurs. It recurs a lot. So how do we stop that? Well, we need base cases, but we'll get to that in a sec when I kind of break down recursive coding. This is essential for more complex tasks where iteration lacks. Trying to do an iterative approach to a binary search tree is great googly moogly. Some of the problems are just so bad, like it's tough. We also need recursion for divide and conquer algorithms, the ones that we know are merge sort and quick sort. Those are pretty dang cool. So yeah, recursive code. Nope, no, not that one. There you go. Great googly moogly. So there's kind of two things that really go on in a recursive function. Obviously, some are much more complicated than that, but the base structure that you can imagine it with is a base case. And in this case, this is what we're using to stop this from happening. If we kept a number tracker going and said 5, so if number is less than 5, then we'd have 1, 2, 3, 4, 5, and then this would all be gone. And then it wouldn't recur. It would momentarily recur. And then it wouldn't be infinite, right? This is your base case. The way that actually, did I go over? Yeah, I do. Okay. So this is your base condition. This is to prevent loops. This is very important. If your base condition is wrong, if your base case is wrong, it will run infinitely. And that is not fun, enjoyable, and not easy to debug. It's kind of like, dang, you know? How many of y'all have gotten an infinitely recursive loop on a CS1 assignment? It's like the worst. Um, but yeah, then there's obviously like the recursive call itself, like the actual call to itself, right? This is the recursive call. There are a few ways that you can do this recursive call, and then kind of everything else in between, like here, same way that I was talking about traversing linked lists. This is kind of like your domain to do all of the functionality that you like want, right? I didn't. This is a screenshot I took from Google. I didn't write the lowercase s. Okay, but yeah, this is kind of just the structure of recursive code. Um, yeah. Also, the call to the function itself, which results in halting. I'm going to go over this in a bit, but the way that I think about recursive functions is here. I'll show you. I'll show you. Right. So conceptually, recursive code can be traced using recursive trees. Now, if you keep in mind, or not keep in mind, if you recall, when I was talking about stacks and there is a function call, like all of these functions that are being called, they're in a stack, right? So when this function returns, when it finally hits its base case and resolves, and it returns, this returns, and then this returns, and then this one returns, and then this one returns. So the recursive call, this recursive call is halted until this one returns. This one is halted until this one returns. If the recursive call, like in the code, is right here, the code that comes after it will not be executed until this is resolved, which means the halting has stopped, which means you have the guarantee that everything after this recursive call has been completed, right? After that code is resolved. So like in the case here, um, it's not good because it's an iterator, right? But you can call it this way and then do some stuff here. All of the functionality you do here after this, you're guaranteed that whatever nsum is doing, it's done to everything after it, right? And I'll go again. I'll show an example with linked lists in a few. But you can, and you probably will, because there are some recursive tracing problems where you have to trace, recursion, right? So they'll give you nsum of 5, and they want to know the result, right? And so basically, all that is the sum 5 times 4 times 3 times 2 times, or 5 plus 4 plus 3 plus 2 plus 1, and you could do this recursively. Drawing it out is a big deal, right? So basically 5 equals 5 plus, and then this is 4, and this drops down, right? And you get the idea. It's a recursion tree. Woo. uh, that was kind of like destructive. I don't know why I did that. Okay, so back to the whole halting thing. Okay, the recursive. So explaining recursion code is hard. I'll try my best in the time we have. Why am I reading this? The recursive call should be seen as the halting. So right here is, we're holding on. We're hanging on, and once this resolves, right? So this is the case where we're freeing a linked list recursively. Once this resolves, so this function would actually be perfectly represented as a linked list. Let's say we're calling this on here, right? So what this is doing is it's saying, okay, well, before I free myself, delete this guy. And then when this guy gets that, he goes, okay, well, before I delete myself, delete this guy, all the way until the base case of null. So this guy's gonna go, hey, before I delete myself, delete this. Oh wait, he's not there. Okay, deleting. And now this guy's gone. And now this guy's gone. But notice how Each and every one of these nodes, after this code has executed, has the guarantee that their next, that head.next or head arrow next, is freed. That is a big concept in recursion. Once you sort of call the function, you could almost think of it as a filtering, depending on the type of function that you're dealing with, right? And so at this point, when we get to free head, we know that everything after it has been freed because of the whole halting thing. It's kind of filtering everything, right? Um, so in the case, delete list function goes all the way down to the list and frees as it goes back up. So as the function call resolves itself, as the function stack pops itself, right? If we were to call free head first, so imagine we are ignoring the use after free error, which is obvious. It would free each node on the way down. So it would free this one, then go here, free this one, then go here, free this one, right? So the perfect example that I have that I came up with was a countdown and a count up function. Okay, so here's one that kind of hopefully can get a better understanding of recursion, right? So in this case, right, we are still having the base case. We want the base case in both, but countdown of size 5 as we go along. So we print the number and then call the next one. So we print the 5, then call this with the next number below it. Then it prints itself, calls it with the next number below it. Then it prints itself, calls with the number below it, prints it, right. Boom. This is pretty simple. It's still recursive, but it feels almost iterative, right? The whole beauty of recursion is when you kind of you leverage this kind of behavior. But the count up function, all it does is it swaps the order of these two. It is the exact same function. They simply just swap the order this was executed. And notice, right? So we put 5. So 5 is in, and it's not going to print itself until the next one has printed it, because again, we're halting. We're saying, okay, I'm not going to print myself until the next number has printed. At which point 4 does the same thing, says, hey, I'm waiting on 3, waiting on 2, waiting on 1. 1 says I'm waiting on 0. 0 is the base case, so 0 resolves itself. 1 goes, okay, I'm going to print 1. 2 sees that 1 went because the halting is completed, right? It's filtered out. The next thing has happened. 2 goes, okay, 1 is done. I'll print. And that goes all the way up to 3. This was the best quick little example I could think of when it comes to recursion. But notice that how big a difference this makes, right? And that's why the free function works this way, because we are making sure we are guaranteeing that at this point, every single element after it has been successfully freed. Because even if ignoring the use after free, if we did this inversed, we would lose access to that like next node, right? So this is basically, it's like, okay, recursion can be kind of hype, right? There's some cool stuff we can do. And so that's why with a lot of binary search tree operations, we'll use recursion, because sometimes we need to know, hey, are we doing the left or the right path? And sometimes that depends on, let's say, left or right path based on the sum of that tree, the subtree. It's like, well, how do you know both of them? Well, you would probably call a function first and then do your type of dealing, right? Stuff like that. So that's really where recursion becomes really, really powerful and really, really strong. Um, and then here's the recursive code tips. Um, Sometimes recursive code. Oh, another one that kind of comes up. Sometimes there are accumulator functions that are recursive. How do you know if they're accumulator or not? Void, void. This one is an integer. This means they want something returned. At which point you are going to have to return something. In these, we didn't have to return anything, but you will have to return something. So what you can do is maybe you want to see the number of nodes that there are, right? So in a linked list or in a tree, you need to make sure you set a base case with the last one that should return 1, right? So basically, if the list.next, if next is null, return 1. So this one's saying, okay, I'm 1 plus this guy. And he's 1 plus this guy. 1 plus, and this one just returns 1 because it's base case. So this is 1 plus 1, which is 2. And this is 1 plus 2, which is 3. Right? So this kind of behavior of saying we can add 1 plus the length of everything after it. Right? So this is that, again, kind of recursive approach, because this one is saying, hey, I'm the length of me plus the rest of the list. And we can do that all the way down until there is no list. So then this guy tells the one to the left of it, hey, I'm 1. This one says, hey, 2, 3, and so on. So this is another example of where we want to use recursion, but it's not a void function. If it is an integer return type, you are going to have to return an integer. Another thing, our null check back here, we simply just return nothing. You cannot do this if it is a integer return type. You need to return a value. It is also acceptable for you to go down to if list equals null, return 0, because it won't count. That is something else you can do. But you are going to have to return a data type. That is the biggest thing for these type of problems, for accumulator problems, right? And so, with that being said, I'm pretty sure we are on our last 2 problems, which is almost right on time for 5 o'clock. Okay. All right. So there are 2 types of recursive problems that they'll give us. They'll give us like an easier one, or they'll give us a hard one, but they'll give us code already filled in. And so what do the hard ones look like? Well, let me go ahead and show you the 10 pointers that they like to throw at us. Poor CS majors or poor souls. Okay, so this one looks all crazy complicated, but if you recognize this, this is actually the flood fill algorithm, which is we kind of went over during recursion, or at least should have went over, making assumptions based on who y'all had. But carrying on. So imagine that a virus is spreading through an area we can model as a 2-dimensional integer array of size n by n, where each value in the array stores the current level of the virus at that grid location. So, for example, this is like a grid. These are all of our different virus levels, 3, 2, 4, 5, 6, etc. If the location that current, if the virus can be activated at a particular location, if that location currently has a virus level that is an even integer, then the virus level in that square increases by 1. And then the activation recursively activates the locations above, below, left, and right of the immediate location. If the virus level in that square was odd, no change occurs and the virus does not spread. Luckily, once the virus in a square increases by 1 due to an activation, it can't increase again. Here's a small example of a before and after picture activating the virus in row 2, column 0. So row 1, or 0, 1, 2, column 0, right here. This is where we're activating it. Okay? So the 2 becomes the 3, so the virus can be activated. So, or no, if that location has a virus level that is an even integer, then the virus increases by 1. So yeah, it increases by 1, right? We then move up, down, left, and right, but left is nothing, so we don't bother, right? This 4 is even, it now becomes a 5. This 6 is even, it now becomes a 7. The 5 is odd, so it remains the same. We now have these 2 that are activated by the virus, which will then go up and right and down and left for all of them, so it's whatever, right? Because of the fact that, let's say, so for example, 2 has already been visited, and now it is odd, that means it's not going to be activated again for the rest of the, like, if you think about it, it won't be activated for as long as this virus runs until everything nulls out, right? Because it's already been turned odd. So that's basically the idea, so that, you don't have to worry too much about infinite loops, because what if this recurses to this node, and then this one to this node, and then this one to this node, and then back here? Well, it's odd now, so it's not going to do anything. So we're going to, we're going to solve this recursive function. I think I might be able to just go fire. Okay, so let's fill this out as a group, one at a time. What is the first if statement going to be? They even give you comments on what they want it to be, which is kind of crazy to me, by the way. They're basically just giving this one away for free. Yep. So first one is going to be call less than 0 or call greater than equal to n, right? And then we're basically going to do the same exact thing, or no, call out of bounds. That is a terrible font color. Bro, y'all get it. Y'all get it. It's not that deep. You get it. Odd square. Y'all know how to check for an odd square. I would hope. So if grid at row at column mod 2 does not equal 0. So that is what's going to go into here. So it's saying, hey, this is an odd square. So these are our two guard clauses. Basically, hey, if it's out of bounds, get rid of it. If it's odd, get rid of it. Kind of like dang, you know. So we got that. And then at this point, what are we doing here? What are we plussing? So remember, the virus goes around, and when it finds an even integer, what does it do to it? It increments that integer. So we're basically going to just increment grid at row column plus plus. And I actually have their plus plus written for me, so I could be even lazier. So the last 4 lines, don't write what it is. Just tell me the gist of what I should do in these last 4 lines. And there's a very big reason of why it's 4 lines exactly. Any buyer? Check right, left, up column. Yep. So you basically just call activate with grid and n, because those will never change. You call one with row -1 column, and then literally this, but you do row -1, row +1, then you have 2 where row is normal, and then column -1, column +1. Imagine these all neatly fit. Oh, they did neatly. Bro, y'all, I'm onto something. That's crazy. So yeah, if we go here to solution, if call, okay, we got the column check down. If grid mod 2 equals 1, oh, what a loser. Okay. Grid row column plus plus, row column, okay. Then basically, yeah, I don't know why they did it that way, but that's fine. We have a +1 -1 on row while column's the same, and then a +1 -1 on column while row is the same. Booyah. We did it, guys. We're like awesome and stuff. So that was our 10-point problem. Let's go look at our 5-point problem, which I think unironically is harder than the 10-point problem. Yeah. Okay. So this one is a little tricky. First thing I want to point out is that it is an integer return type. So we are going to have this like accumulator thing going on. Okay. So let's read it. Consider the problem of a frog jumping out of a well. Initially, n feet below the top of initially the frog is n feet below the top of the well. When the frog jumps up, it elevates u feet. If a jump gets the frog to the top of the well or past it, the frog escapes the well. If not, unfortunately, the frog slips down by d feet before clinging to the side of the well. Note that d is always less than u, so you can't go backwards. Amen. Write a recursive function that takes in positive integers n, u, and d and returns the number of times the frog must jump to get out of the well. Will we go over permutations? Not today, unfortunately. We're running low on time, but I did realize I probably should have thrown that in there. Unfortunately, y'all will have to watch that on your own, which is fine because I had to watch it on my own too. So y'all get to start. No, I'm kidding. I apologize, but no, we will not be going over permutations today. Or the rest of the workshop. We didn't have anything particularly planned for permutations. But back to the problem. For example, so I'm going to go ahead and draw this out because it's the best to kind of visualize things. So for example, if n equals 10 feet, so this is the actual height of here, our little frog, we'll represent him as a diamond, right? A little diamond. And then if n equals 10, u equals 5. So our frog can jump 5 feet up because he's awesome and like super cool and stuff. But he also slides 3 feet down, which is kind of sad if you think about it. It's like a messed up world we live in. So it should return 4. Why? Well, okay. The frog goes up 5 feet, clings here, comes down 3. He's now at 2 feet. The frog goes up 5 to 7, comes down 3. He's now at 4. So that's 2 jumps. The frog goes up 5 to 9, comes down 3. That gets him at 6. That's 3 jumps. And then eventually he jumps 5 feet. He's at 8. That clears the gap. So no sliding, and that's 4 jumps. So we're going to get int num jumps, okay? What is our base case here? What is the base case that y'all can give me? Because all recursive code should start with some sort of base case. What is the case where we finally stop having to call our code? No, it is not n less than u. That's we want to know when it ends, not when it keeps going. Because if we kept n less than u, that means we're just saying stop the code when he is beneath, or no. U is the upwards jump that he has, not the current position that he's in. So you'd never break out. It's saying that's basically saying if you can make this in one jump. Yeah, you don't want to do that. The base case, no, I haven't seen any yet. So let's think about it this way. So if our current upwards force is greater than or equal to the amount of room left, right? So saying that our upwards force is less or is greater than the amount of wall that we have left. That means, okay, we can clear this. So we're going to want to return 1 because that's a jump. That means we have 1 jump to get out of here, right? So you were close, yes. If u is greater than or equal to n, it says that pretty sure if a jump gets the frog to the top of the well or past it, so it can be equal. That's why. So if u is greater than or equal to n, return 1. And then here's what we're going to do. We're going to return 1 because remember, we're running the accumulator, but we're going to call num jumps again. And the amount of wall left over, right, is going to be equal to the current wall minus our upwards jump minus the downwards jump. So remember how here, right, we went up 5 feet and down 3 feet. That means we made a gain of up minus down, 5 minus 3. Each time we did a jump, the wall got shorter by 2 feet. So basically we're saying, hey, jump, that's going to be n minus our upwards minus our downwards force. So in this case, it's 2, right? So this is the new height of the wall that's getting passed in. And then what else what are the parameters for u and d that I should put in? Just u and d. Perfect, because our up and jump stays the same, right? And so basically what this is going to be doing now is it's going to keep subtracting. So the first time this function is called with our situation, right? Since our u was 5 and our d was 3, so we're getting it called for the first time with 10, 5, 3 in the last example, right? And then we make our jump. That's going to be 8, 5, 3. We're going to make our jump again. That's going to be 6, 5, 3 left over, right? Because we're subtracting by 2 every time. And then the fourth iteration, let me see. Right here, it's going to be 4, 4, 5, 3. This is going to work. So this is going to return 1 plus 1 plus 1 plus, and then this is base case, so 1, right? So boom. Does that make sense? Because at this point, 5 is greater than or equal to 4. So we just returned 1 instead of returning 1 plus something after it. So that ends up being 1. And that basically just does this. Yep. And so that's kind of the approach. Each time they jump, the amount of wall that they need to continue jumping gets less and less and less. And your base case is they actually make it out and jump over the wall. They actually get over the wall, which is if your upwards force is greater than the remaining piece of wall. And so we just continue decrementing the wall in each call and creating that iterator of 1 plus every time we do it. So that ends us exactly at 5, which is crazy. Because I haven't ran through this entire thing before. That was the first shot. So I hope y'all enjoyed that. I hope that was good. We will be back tomorrow for the recording be posted on Discord. Eventually, Zoom does require time to index these transcripts. So it takes like we did like a mock little thing that would last like 50 minutes, and it took Zoom about like 30 to 45 minutes. I have an email script set up so that it'll text me as soon as I get that Zoom meeting out. I'll go ahead and make the recording public. It's going to be a Zoom link. I'm not going to put any password on it. I'm not going to put anything like that, but it will be out. I'll make an announcement for it soon. And then I will also post the slides that we have gone over thus far. I don't want to post the upcoming slides because they may change tonight, or you may want to get eager and go ahead and like maybe confuse yourself more or something like that. So just I'm going to share the slides that we went over today. And then last but not least, solution. It's exactly what we got, right? Boom. We're awesome. Appreciate all the support, all the appreciation in chat. Y'all are awesome. We'll see you back tomorrow. And happy studying. I'll make an announcement when everything is out.